Hello there, and welcome to the Sleepy Professor. Tonight, we are exploring something quietly extraordinary: the chemistry of everyday life, not as a distant subject confined to laboratories, but as the invisible architecture of every moment you live. This is the story of molecules in conversation, water finding water, proteins folding into purpose, light breaking bonds that have held for years, atoms trading electrons in your kitchen, your clothes, the air you are breathing right now. What seems solid and still is actually vibrating, reacting, transforming at speeds too small and too fast to see. Yet these transformations create everything you touch, taste, smell, and depend upon. The brown crust on your morning toast, the way soap lifts grease from a plate, the green patina on old copper, the warmth of a wool sweater. All of it is chemistry, patient and relentless, working without fanfare every single day. If you enjoy these gentle journeys through science, I invite you to subscribe, leave a kind word below, or simply share this with someone who might find their way here. It helps other curious, sleepy minds discover these late-night explorations, one peaceful soul at a time. But for now, there is nothing to do but settle. Let your body sink into whatever is supporting you. Let your shoulders drop away from your ears. Allow your jaw to unclench. Feel the weight of your head resting heavily, completely. Let your breathing slow and deepen, asking nothing of it, simply noticing its rhythm. And let your thoughts begin to quiet as we step into this hidden molecular world together. Let us begin. Water is so common that it can feel invisible, yet it is one of the most unusual molecules in nature. Each water molecule is a small bent structure, one oxygen atom holding two hydrogen atoms at an angle. That angle matters because it creates an uneven distribution of charge. The oxygen side is slightly negative. The hydrogen side is slightly positive. This imbalance allows water molecules to reach toward one another, forming weak attractions called hydrogen bonds. These bonds are temporary. They form and break trillions of times each second, yet their collective effect is profound. Hydrogen bonds hold water together with just enough strength to create surface tension, to make ice less dense than liquid water, and to allow water to dissolve an astonishing variety of substances. Life depends on this dance. Proteins fold into their working shapes because water pushes oily parts inward and pulls charged parts outward. DNA strands pair because hydrogen bonds link the bases gently, allowing them to unzip when needed. Without hydrogen bonding, water would boil at far lower temperatures, and life as we know it could not exist. The fascinating part is that something so small and fleeting can hold together the entire architecture of biology. A weak bond, repeated endlessly, becomes the foundation of everything alive. Most substances become denser when they freeze. Their molecules pack more tightly as they lose energy and movement. Water does the opposite. When water freezes, hydrogen bonds lock the molecules into a rigid hexagonal lattice. That structure holds each molecule slightly farther apart than in liquid water. The result is ice that is less dense than the water beneath it. This peculiarity has consequences that ripple through the entire planet. When lakes and ponds freeze in winter, ice forms at the surface and stays there. The water below remains liquid, insulated by the ice above. Fish, plants, and microorganisms survive the cold months in that hidden layer. If ice sank, bodies of water would freeze from the bottom up. Many would freeze solid, and winter would become a season of mass extinction. The hexagonal structure of ice is also why snowflakes have six-fold symmetry. Each flake grows as water vapor adds molecules to the lattice, following the angles dictated by hydrogen bonds. The same chemical principle that keeps oceans from freezing solid also creates the intricate beauty of snow. The remarkable part is that a simple angle, 104.5 degrees between hydrogen atoms, shapes winter itself and protects life in the process. Water's surface behaves like a stretched film, strong enough to support objects that should sink. This phenomenon is surface tension, and it arises because water molecules at the surface have fewer neighbors to bond with. Molecules below the surface are pulled equally in all directions by hydrogen bonds. Molecules at the surface are pulled only downward and sideways. This creates an inward pull that contracts the surface into the smallest possible area. The result is a skin of tension that can support weight if distributed carefully. Water striders and other insects take advantage of this. Their legs are covered in waxy hairs that repel water. When they step onto the surface, they dent it slightly without breaking through. The surface tension pushes back, holding them up. The insect floats not on the water itself, but on the elastic boundary between water and air. Surface tension also explains why water forms droplets rather than spreading into thin sheets. It is why you can fill a glass slightly above the rim without spilling, the water bulging upward in a dome. And it is why small objects like paper clips can float if placed gently, despite being denser than water. The wonder is that this strength comes not from rigidity, but from attraction. Molecules pulling on one another create a boundary that feels almost solid, yet remains liquid and alive. Logic suggests that cold water should freeze before hot water. After all, it has less distance to travel to reach freezing temperature. Yet under certain conditions, hot water can freeze faster. This counterintuitive phenomenon is called the Mpemba effect, named after a Tanzanian student who observed it while making ice cream in the 1960s. Several factors may contribute. Hot water evaporates more quickly, reducing the total volume that needs to freeze. It may also lose heat faster through convection currents that circulate the water and bring warmer portions into contact with cold air. Dissolved gases escape more readily from hot water, which can alter the freezing process. The effect is inconsistent and depends on container shape, water purity, and environmental conditions. Some experiments replicate it easily, others do not. Despite being observed for centuries, the Mpemba effect remains incompletely understood. Aristotle mentioned it, Francis Bacon noted it, Yet scientists still debate the precise mechanisms. This makes it a humbling reminder that even simple systems like cooling water can hold surprises. The fascinating aspect is not just that hot water can freeze faster, but that everyday phenomena can still puzzle us. Even water, studied for millennia, keeps a few secrets. Water dissolves more substances than any other liquid, earning it the title of universal solvent. This ability comes from its molecular polarity. The oxygen end of each water molecule carries a slight negative charge. The hydrogen end carries a slight positive charge. When water encounters a substance like salt, these charges go to work. Salt is made of positive sodium ions and negative chloride ions held together by strong ionic bonds. When salt meets water, water molecules surround each ion. The negative oxygen ends cluster around sodium. The positive hydrogen ends cluster around chloride. These attractions pull the ions away from the crystal and into solution. The salt dissolves, not because the ionic bonds break entirely, but because water molecules stabilize the separated ions in solution. Water dissolves sugars, acids, alcohols, and many other compounds through similar interactions. It pulls apart molecules, spreads them evenly, and keeps them suspended. This property is essential for life. Blood is mostly water, carrying dissolved nutrients, gases, and waste products. Cells are filled with water that holds proteins, salts, and genetic material in working proximity. The poetic part is that water achieves this through generosity. It shares its charge, offers stability, and creates a medium where chemistry can happen. Life exists in solution, and water is the solvent that makes it possible. Not all water is identical. Most water molecules contain ordinary hydrogen, which has one proton and one electron. But a tiny fraction, about 1 in every 3,200 molecules, contains deuterium instead. Deuterium is hydrogen's heavier sibling. Its nucleus holds one proton and one neutron, doubling its mass. Water made with deuterium is called heavy water, or D2O. Heavy water looks like normal water. It is colorless, odorless, and wet. But it is about 11% denser. Ice made from heavy water sinks in regular water. And remarkably, heavy water tastes slightly sweet to many people. Scientists are not entirely sure why. The deuterium may interact differently with taste receptors, or it may alter the structure of the water itself in subtle ways. Heavy water occurs naturally in oceans and rivers, mixed thoroughly with regular water. It can be separated through repeated distillation or electrolysis. Pure heavy water is used in some nuclear reactors as a neutron moderator. It is also valuable in scientific research as a tracer because deuterium behaves chemically like hydrogen, but can be detected separately. The striking part is that one extra neutron, invisible and buried in the nucleus, changes how water feels on your tongue. Chemistry reaches into perception through the smallest adjustments. Water normally freezes at 0 degrees Celsius, but under the right conditions, it can remain liquid well below that temperature. This is called supercooling. It happens when water is very pure and the container is very smooth. Freezing requires a nucleation site, a tiny imperfection or particle where ice crystals can begin forming. Without such a site, water molecules continue moving as a liquid, even though they have enough thermal energy to freeze. Supercooled water is unstable. The slightest disturbance, a vibration, a speck of dust, or even a whisper can trigger instant crystallization. The water snaps into ice within seconds, releasing the heat that should have been lost gradually during freezing. You can sometimes supercool bottled water in a freezer, then tap the bottle sharply and watch ice spread through the liquid like a visible shockwave. Supercooled water exists in nature. Clouds often contain supercooled droplets that freeze instantly when they hit an aircraft or a tree branch. This creates rime ice, a feathery coating that builds windward on cold surfaces. The same phenomenon contributes to freezing rain, where supercooled droplets freeze on contact with the ground. The wonder is that water can hover in an in-between state, liquid by technicality, waiting for permission to become what it should already be. Heat capacity measures how much energy is needed to raise a substance's temperature. Water has one of the highest heat capacities of any common material. It takes a great deal of energy to warm water even slightly, and water releases that energy slowly as it cools. This property arises from hydrogen bonding. Energy added to water does not immediately increase molecular motion. Much of it goes into breaking and reforming hydrogen bonds. This thermal stability has planetary consequences. Oceans absorb enormous amounts of solar energy during summer, warming slowly. They release that energy gradually through autumn and winter, moderating temperature swings. Coastal regions experience milder climates than inland areas at the same latitude because nearby water buffers temperature extremes. Without water's high heat capacity, days would be scorching and nights frigid. Your body also relies on this property. Water makes up about 60% of your mass. That water resists rapid temperature changes, helping maintain a stable internal environment. Sweating cools you efficiently because water absorbs body heat as it evaporates, carrying energy away. The astonishing part is that water's reluctance to change temperature shapes weather patterns, ocean currents, and the rhythm of seasons. Stability at the molecular level becomes stability across the entire planet. When you sear a steak, toast bread, or roast coffee beans, a complex transformation occurs at the surface. This is the Maillard reaction, a cascade of chemical changes between amino acids and reducing sugars. The reaction begins when heat brings these molecules into close contact. They bond, break apart, and recombine into hundreds of new compounds. Many of these compounds are brown pigments called melanoidins. Others are volatile molecules that create the rich, savory aromas we associate with cooked food. The Maillard reaction is not caramelization. Caramelization involves only sugars. The Maillard reaction requires both amino acids from proteins and sugars. It also requires heat, typically above 140 degrees Celsius. Below that threshold, the reaction proceeds too slowly to produce noticeable browning. Above it, the reaction accelerates, deepening color and flavor rapidly. This chemistry explains why a boiled steak is pale and bland, while a seared steak is dark and savory. Boiling water never exceeds 100 degrees Celsius, too cool for the Maillard reaction. A hot pan reaches temperatures where the reaction flourishes. The same principle applies to bread crusts, roasted vegetables, and grilled meats. The remarkable part is that this one reaction generates thousands of different flavor compounds. Each combination of protein and sugar produces a unique profile. The Maillard reaction is not one process, but a family of transformations, each one adding depth to the simple act of cooking. Sugar tastes sweet and dissolves easily in water, but when heated to high temperatures, it transforms entirely. This process is caramelization. It begins around 160 degrees Celsius when sugar molecules start breaking apart. The heat ruptures chemical bonds, splitting sucrose into glucose and fructose. Those simpler sugars then decompose further, losing water molecules and forming new compounds. Some of these compounds are bitter, others are nutty, buttery, or toasted. Together, they create the complex flavor of caramel. The color deepens as well, progressing from pale gold to amber to dark brown. The darker the caramel, the more bitter and less sweet it becomes. Eventually, if heated too long, the sugar burns completely into black, acrid char. Caramelization is not the same as melting sugar. Melting happens first, at a lower temperature, when sugar crystals dissolve into liquid. Caramelization happens afterward, when that liquid begins to decompose chemically. The two processes are distinct, though they occur in sequence. Caramel appears in countless foods. Crème brûlée owes its glassy topping to caramelized sugar. Dark beer gains color and flavor from caramelized malts. Even the browning on roasted onions involves some caramelization alongside the Maillard reaction. The beauty is that heat alone, without adding anything, can turn simple sweetness into a spectrum of flavors, bitter and complex and layered. Baking soda and baking powder are both leavening agents, but they function in different ways. Baking soda is pure sodium bicarbonate. It is a base, and it reacts with acids to produce carbon dioxide gas. When you add baking soda to buttermilk, yogurt, vinegar, or lemon juice, bubbles form immediately. That gas becomes trapped in batter, creating lift and lightness as the food bakes. Baking powder is more complex. It contains baking soda, but it also includes a powdered acid, usually cream of tartar. This means baking powder does not need an external acid to react. It activates when moistened. Most baking powders are double-acting, meaning they release some carbon dioxide when wet and more when heated. This gives bakers more control over timing. Using the wrong one can ruin a recipe. Too much baking soda without enough acid leaves a soapy, metallic taste. Too little leavening produces dense, heavy results. The balance matters because the amount of carbon dioxide generated determines how much the batter rises. The fascinating part is that both involve the same chemical, sodium bicarbonate, yet they behave so differently depending on what surrounds them. Context shapes chemistry. A single ingredient can produce entirely different results based on what it meets in the bowl. Salt does more than add flavor to meat. It changes the physical structure of proteins through a process called denaturing. Proteins are long chains of amino acids folded into specific three-dimensional shapes. Those shapes are held together by weak bonds between different parts of the chain. When salt is added to meat, sodium and chloride ions disrupt those bonds. As the protein structure loosens, the tightly coiled chains begin to unwind. This makes the meat more tender because the rigid network of proteins becomes softer and more pliable. Salt also helps the meat retain moisture. Denatured proteins can hold more water molecules, so salted meat stays juicier during cooking. This is why brining works. Soaking meat in a saltwater solution allows salt to penetrate deeply, denaturing proteins throughout. The result is meat that is both more tender and more flavorful. Dry brining, rubbing salt directly onto the surface, achieves a similar effect more slowly. The effect is not instant. Salt needs time to diffuse into the tissue and interact with proteins. That is why salting meat an hour or more before cooking produces better results than salting just before it hits the heat. The wonder is that a simple mineral can reach into the molecular structure of tissue and reshape it. Salt is not just seasoning. It is a tool that changes texture from the inside. Vegetables contain pigments that respond to pH, the measure of acidity or alkalinity. One common group of pigments is anthocyanins, found in red cabbage, purple cauliflower, and berries. Anthocyanins are pH indicators. They turn bright red in acidic conditions and shift toward blue or gray in alkaline conditions. Adding a splash of vinegar to red cabbage keeps it vibrant. Adding baking soda turns it an unappetizing gray-blue. Green vegetables contain chlorophyll, which also reacts to pH. Acids turn chlorophyll a dull olive green by replacing magnesium at the center of the molecule with hydrogen. Bases, on the other hand, can preserve or even brighten green color temporarily, though they often turn vegetables mushy by breaking down cell walls. Traditional cooks sometimes add a pinch of baking soda to green beans to keep them bright. Modern cooks usually avoid this because the trade-off is a loss of texture and nutrients. Instead, they blanch vegetables briefly in boiling water, then plunge them into ice water to halt cooking. This preserves both color and crispness without altering pH. The striking part is that color is not fixed. It is chemistry responding to its environment. A vegetable changes its appearance based on what it encounters in the pot, and pH is the invisible hand guiding that transformation. Whipped cream is a foam, a structure where gas is dispersed throughout a liquid. It forms because cream contains both fat globules and proteins. When you whip cream, you force air into it. The mechanical action also partially breaks down the fat globules. The fats begin to clump together, forming a loose network. At the same time, proteins in the cream unfold and help stabilize the air bubbles. The result is a structure that holds its shape. Air bubbles are surrounded by fat and protein, preventing them from merging and escaping. The cream becomes thick, light, and voluminous. If you whip too little, the structure does not form and the cream stays liquid. If you whip too long, the fat clumps too much and you end up with butter and buttermilk instead. Temperature matters enormously. Cold cream whips more easily because the fat is solid and easier to break into stable pieces. Warm cream is more difficult to whip because the fat stays liquid and does not form a network. This is why recipes often call for chilling the bowl and beaters. The fascinating part is that whipped cream is not really solid or liquid. It is a carefully balanced structure, held together by interactions between air, fat, and protein. Stop whipping at the right moment, and you have something impossibly light that melts on the tongue. Yeast is a single-celled fungus that consumes sugar for energy. In the presence of oxygen, yeast breaks down sugar completely into carbon dioxide and water. But in the absence of oxygen, yeast switches to fermentation. It converts sugar into ethanol and carbon dioxide, producing less energy, but allowing the yeast to survive. Bakers exploit this process. When yeast is mixed into dough, it begins fermenting the sugars present in the flour. Carbon dioxide gas is released and becomes trapped in the gluten network, causing the dough to rise. The alcohol produced evaporates during baking, leaving behind complex flavors developed during fermentation. Brewers and winemakers use the same process, though they care more about the alcohol than the gas. Yeast is added to a sugary liquid, grape juice or malted grain, and fermentation proceeds over days or weeks. The carbon dioxide escapes or is captured separately. The alcohol remains, along with flavor compounds produced as byproducts of fermentation. Different yeast strains produce different results. Bread yeast and wine yeast are the same species, Saccharomyces cerevisiae, but they have been bred for different behaviors. Bread yeast rises quickly. Wine yeast tolerates higher alcohol levels. Each strain is a specialist. The wonder is that this microscopic organism has shaped human culture for thousands of years. Bread, beer, and wine all exist because yeast turns sugar into gas and alcohol. Fermentation is ancient chemistry, still working the same way it always has. Wheat flour contains two main proteins, gliadin and glutenin. On their own, they are inactive. But when flour is mixed with water and kneaded, these proteins hydrate and begin linking together. They form long, elastic strands called gluten. Gluten is what gives bread dough its stretchiness and allows it to trap gas bubbles during rising. The more you knead, the more gluten develops. This is desirable for bread, where a strong gluten network creates structure and chew. It is less desirable for tender baked goods like cakes and pastries. For those, minimal mixing keeps gluten development low, resulting in a softer, more delicate crumb. Gluten's elasticity comes from its molecular structure. The proteins are long chains that can slide past one another and stretch without breaking. When you pull dough, gluten strands extend. When you release it, they contract. This elasticity is also what makes dough tricky to roll out. It fights back, shrinking as you try to flatten it. Resting dough allows gluten to relax. The proteins settle into a less dense configuration, making the dough easier to shape. This is why pizza dough is often made ahead and chilled. The rest period improves both texture and handling. The remarkable part is that two proteins, invisible in the flour, become a flexible network simply by meeting water. Structure emerges from mixture, and that structure becomes the foundation of countless foods. Oil and water do not mix naturally. Oil is nonpolar, meaning its molecules have no charged regions. Water is polar, with positive and negative ends. Opposite natures cause them to separate, oil floating in distinct layers above water. But with the right help, you can force them to mix. This is called an emulsion. Mayonnaise is a classic emulsion. It combines oil, water from vinegar or lemon juice, and an emulsifier, egg yolk. The egg yolk contains lecithin, a molecule with one end that loves water and another that loves oil. When you whisk oil into egg yolk and vinegar, lecithin molecules arrange themselves at the boundary between oil droplets and water. The water-loving end faces outward into the vinegar. The oil-loving end faces inward into the oil droplet. This stabilizes the mixture, preventing oil and water from separating. The key to making mayonnaise is adding oil very slowly at first. If you add too much oil too quickly, there is not enough emulsifier to surround all the droplets. The emulsion breaks, and you are left with a curdled mess. Once an emulsion is established, you can add oil more rapidly because the existing structure helps incorporate new oil. Other emulsions include milk, vinaigrettes, and hollandaise sauce. Each relies on an emulsifier to bridge the gap between oil and water, creating a stable mixture where none should exist. The fascinating part is that chemistry can overcome fundamental incompatibilities. With the right mediator, opposites not only meet, they stay together. Eggs contain proteins that remain dissolved in water at room temperature. But when heated, these proteins begin to unfold. The heat gives molecules enough energy to break the bonds, holding them in compact shapes. As they unfold, proteins expose regions that are sticky. These regions grab onto neighboring proteins. The proteins link into networks, trapping water and transforming from liquid to gel. This is coagulation. Different egg proteins coagulate at different temperatures. Egg white proteins begin setting around 60 degrees Celsius and fully solidify by 65 degrees. Egg yolk proteins start coagulating at 65 degrees and firm up around 70 degrees. This difference allows cooks to control texture. Low, gentle heat produces soft, creamy scrambled eggs because the proteins coagulate slowly and form small curds. High heat produces rubbery eggs because proteins coagulate rapidly and squeeze out water. Custards rely on this precise temperature control. A crème brûlée is mostly cream and egg yolks, heated gently until the yolk proteins just begin to network. Heat them too much and the custard curdles. Heat them too little and it stays liquid. The sweet spot is narrow, usually between 70 and 80 degrees Celsius. The beauty of egg cookery is that it demonstrates molecular precision in the kitchen. A few degrees make the difference between silky and rubbery. You are not just heating food, you are managing a transformation at the molecular level, and the protein networks respond with exact predictability. Bananas do not ripen alone. As a banana ripens, it releases ethylene, a simple hydrocarbon gas with the formula C2H4. Ethylene is a plant hormone that triggers ripening in many fruits. It signals cells to produce enzymes that break down cell walls, convert starches to sugars, and soften flesh. When one banana releases ethylene, nearby fruits detect it and begin ripening as well. This is why placing a banana in a bag with unripe avocados or tomatoes speeds ripening. The confined space concentrates ethylene, amplifying its effect. It is also why bananas in a bunch ripen together. They share ethylene in a feedback loop, each fruit encouraging the others. Farmers exploit this by picking bananas while they are still green and hard. The bananas are shipped unripe, then exposed to ethylene gas in ripening rooms just before reaching stores. This allows controlled timing. Without ethylene management, bananas would ripen unpredictably during transport and spoil before reaching consumers. Some fruits, like berries and grapes, do not respond to ethylene. They are called non-climacteric fruits. Others, like apples, pears, and peaches, ripen dramatically in its presence. These are climacteric fruits. Knowing which is which helps in storage. Keep ethylene-producing apples away from lettuce, for example, or the lettuce will wilt and brown faster. The striking part is that ripening is a conversation. Fruits talk to each other using a simple molecule, and the message spreads invisibly through the air. Cutting an onion releases a chain reaction of chemistry that ends in tears. Onions contain sulfur compounds stored in their cells. When a knife ruptures those cells, enzymes are released that convert the sulfur compounds into a volatile gas called synpropanethyl S oxide. This gas drifts upward and dissolves in the moisture on the surface of your eyes. Once in the eye, the gas reacts with water to form sulfuric acid. Your eyes detect the acid as an irritant and respond by producing tears to flush it away. The sharper the knife, the fewer cells are crushed, and the less gas is released. Dull knives mangle more cells, releasing more irritant. Chilling onions before cutting slows the enzymatic reaction, reducing the amount of gas produced. Some people wear goggles or run a fan to blow the gas away. Others cut onions under running water to wash away the compounds before they become airborne. Each method aims to prevent the gas from reaching the eyes. The sulfur compounds exist because onions evolved them as a defense against herbivores. The compounds are toxic to insects and deter animals from eating the bulb. Humans tolerate the irritation because we value the flavor those same sulfur compounds provide. We accept the tears as a cost of the chemistry that makes onions pungent and savory. The wonder is that cooking transforms these harsh compounds entirely. Heat breaks them down into sugars and milder sulfur notes. turning sharp and tear-inducing into sweet and mellow. Chocolate is a complex mixture of cocoa solids, cocoa butter, and sugar. When chocolate melts, the cocoa butter can crystallize into 6 different forms when it cools. 5 of these forms are unstable. They produce chocolate that is soft, crumbly, or develops a white bloom on the surface. Only one crystal form, called Form 5 or beta crystals, produces chocolate with a glossy appearance, a satisfying snap when broken, and a smooth melt on the tongue. Tempering is the process of encouraging cocoa butter to crystallize in this desirable form. It involves carefully controlling temperature. First, chocolate is melted completely, usually to around 45 degrees Celsius. This destroys all existing crystals. Then it is cooled to about 27 degrees, which encourages stable crystal formation. Finally, it is gently reheated to about 10 degrees, which melts away any unstable crystals while preserving the good ones. Once properly tempered, the chocolate can be molded or used for coating. It sets quickly with a hard, shiny finish. Untempered chocolate remains soft and develops streaky white patches as the cocoa butter separates and forms irregular crystals on the surface. The fascinating part is that cocoa butter is polymorphic. The same fat can arrange itself in multiple ways, and the arrangement determines everything about how the chocolate behaves. A difference of a few degrees during cooling decides whether chocolate is professional quality or disappointingly dull. Coffee brewing is an extraction process. Ground coffee contains hundreds of soluble compounds, oils, acids, sugars, and bitter alkaloids. Hot water dissolves these compounds at different rates. Smaller molecules dissolve quickly. Larger molecules dissolve more slowly. The goal is to extract enough of the desirable flavors without pulling out too many of the bitter, astringent compounds that emerge later. Under extraction produces sour, weak coffee. Not enough contact time means water dissolves only the acids and lightest flavors. Over extraction produces bitter, harsh coffee. Too much contact time allows water to pull out large tannins and caffeine-related compounds that taste unpleasant. Grind size controls extraction speed. Fine grounds have more surface area, so water extracts compounds quickly. Coarse grounds have less surface area and extract slowly. Espresso uses very fine grounds and brief contact time, usually 25 to 30 seconds. French press uses coarse grounds and long contact time, around 4 minutes. Each brewing method is calibrated to balance grind size, water temperature, and contact time. Water temperature matters as well. Hotter water extracts faster and more completely. But water that is too hot, above 96 degrees Celsius, can extract unpleasant, bitter notes. Water that is too cool, below 88 degrees, produces weak, under-extracted coffee. The remarkable part is that coffee brewing is not cooking. It is selective dissolution. You are choosing which molecules to pull from the grounds and which to leave behind. Mastery lies in knowing when to stop. Bread rises because gluten traps carbon dioxide from yeast. When yeast ferments sugars in the dough, it produces carbon dioxide gas as a byproduct. In the absence of gluten, that gas would simply escape into the air. But gluten forms an elastic network throughout the dough. As gas bubbles form, they press against the gluten strands. The strands stretch, creating pockets that hold the gas. As fermentation continues, more gas accumulates. The dough expands. Gluten keeps stretching, accommodating more and more gas until the structure reaches its limit. If the dough rises too long, the gluten network weakens and collapses. The dough deflates. This is why timing matters in bread making. You want to bake the dough after it has risen, but before the gluten loses its strength. Baking transforms the structure permanently. Heat causes the starches in flour to gelatinize, absorbing water and becoming firm. The gluten proteins coagulate, setting into a solid network. The yeast dies, stopping gas production. The result is bread, a solid foam with a network of air pockets locked in place. Different breads have different crumb structures depending on hydration, kneading, and fermentation time. A baguette has an open, irregular crumb with large holes. Sandwich bread has a fine, even crumb with small, uniform holes. Both are gluten networks holding gas, but the details of their creation produce very different textures. The beauty is that bread is architecture built by biology. Yeast provides the material. Gluten provides the structure. Heat makes it permanent. When you cut an apple, the flesh quickly turns brown. This is enzymatic browning, a chemical reaction between oxygen in the air and phenolic compounds in the apple. When cells are damaged, enzymes called polyphenol oxidases are released. These enzymes catalyze the oxidation of phenols into quinones. Quinones are colorless at first, but they quickly react with amino acids and other compounds to form brown melanin pigments. Citric acid prevents this browning through multiple mechanisms. First, it lowers pH. Polyphenol oxidase enzymes work best at neutral pH and slow down significantly in acidic conditions. Second, citric acid is a reducing agent. It donates electrons to quinones, converting them back to phenols before they can form brown pigments. Third, citric acid can chelate copper ions that the enzyme needs to function. A squeeze of lemon juice or a dip in acidulated water keeps cut apples, pears, and avocados looking fresh for hours. The fruit still oxidizes eventually, but the process is dramatically slowed. Commercial food processors use citric acid or ascorbic acid, vitamin C, for the same purpose. Pre-cut apple slices in packages stay white because they have been treated with an acid solution. The striking part is that browning is not decay. It is oxidation, a chemical change that happens almost instantly when cells are ruptured. The fruit is not going bad. It is reacting with air. Acid interrupts that reaction by changing the chemical environment. Sous vide is French for under vacuum. The technique involves sealing food in a plastic bag, removing the air, and cooking it in a temperature-controlled water bath. The water is held at a precise temperature, often far lower than traditional cooking methods. A steak might be cooked at 55 degrees Celsius for an hour or more. This precision matters because different proteins denature at different temperatures. Myosin, a muscle protein, begins to coagulate around 50 degrees. Actin, another muscle protein, coagulates around 66 degrees. Collagen, the connective tissue, breaks down into gelatin around 70 degrees. By holding food at a specific temperature, you can control which proteins transform and which remain intact. A steak cooked sous vide at 55 degrees is uniformly medium rare from edge to edge. Traditional methods apply high heat to the outside, creating gradients. The surface is well done, the interior is rare, and only a thin band is the desired doneness. Sous vide eliminates the gradient. Every part of the steak reaches the same temperature, producing even texture throughout. The technique also prevents overcooking. In an oven, food continues heating past the target temperature because the surrounding air is much hotter. In a water bath set to 55 degrees, the food cannot exceed 55 degrees, no matter how long it sits. The fascinating insight is that cooking is protein chemistry. Heat is not just a tool, it is a signal that tells proteins when to change. Sous vide lets you speak that language with extraordinary precision. Soap is one of humanity's oldest chemical inventions. It works because soap molecules are amphiphilic, meaning they have two distinct ends with opposite properties. One end is hydrophilic, attracted to water. It consists of a charged carboxylate group that dissolves easily in water. The other end is hydrophobic, repelled by water. It consists of a long hydrocarbon chain that dissolves in oils and fats. When soap is added to water containing grease, the hydrophobic tails burrow into the grease, while the hydrophilic heads remain in the water. Soap molecules arrange themselves around each droplet of grease, forming structures called micelles. The grease is now surrounded by a layer of soap, with water-loving heads facing outward. This allows the grease to be suspended in water and rinsed away. Without soap, grease, and water do not mix. Grease clings to surfaces and resists rinsing. With soap, grease is emulsified, broken into tiny droplets that can be washed away. This same principle works on your hands, on dishes, and on clothing. Traditional soap is made by reacting fats with a strong base like lye, sodium hydroxide. This process is called saponification. The chemical reaction breaks down triglycerides in the fat into glycerol and fatty acid salts. Those fatty acid salts are soap. The wonder is that something so simple, a molecule with two opposite ends, can bridge the gap between oil and water. Soap is a molecular diplomat, making peace between substances that naturally repel each other. Detergents are synthetic cleaning agents developed to overcome soap's limitations. Soap performs poorly in hard water, which contains calcium and magnesium ions. These ions react with soap to form insoluble precipitates, the soap scum that coats bathtubs and leaves residue on clothing. Detergents are structurally similar to soap, but are designed to avoid this problem. Like soap, detergents have a hydrophobic tail and a hydrophilic head. But the head group is different. Instead of a carboxylate, detergents often use sulfate or sulfonate groups. These do not react with calcium or magnesium. so they work effectively in hard water without forming scum. Detergents can also be tailored for specific tasks. Laundry detergents contain enzymes that break down protein stains like blood and grass. Dishwasher detergents contain builders that soften water and enhance cleaning. Some detergents produce lots of suds. Others are formulated to be low sudsing for use in high efficiency machines. The chemistry is similar to soap, but the details matter. Small changes in molecular structure produce large changes in performance. Detergents represent an improvement, not because the principle is different, but because chemists refined the design to work in more situations. The fascinating part is that detergents are custom molecules. They do not exist in nature. They were invented to solve specific problems, and they succeed by being precisely what soap cannot be. Bleach is a powerful oxidizing agent. The most common household bleach is sodium hypochlorite dissolved in water. When bleach contacts a stain, it donates oxygen atoms to the molecules that create color. These molecules, called chromophores, absorb light at specific wavelengths, which is what makes them appear colored. Oxidation breaks the chemical bonds that allow chromophores to absorb light. Once the bonds are broken, the molecules no longer absorb visible light. The stain becomes colorless. Bleach does not remove stains by dissolving them or lifting them away. It chemically alters them so they no longer produce color. The stain is still there at a molecular level, but it has been transformed into a colorless compound. Bleach also kills bacteria, viruses, and fungi. Oxidation disrupts the proteins and nucleic acids that microorganisms need to survive. This makes bleach an effective disinfectant, as well as a whitening agent. However, bleach is harsh. It can damage fabrics, irritate skin, and produce toxic fumes when mixed with acids or ammonia. Alternative bleaches exist. Oxygen bleach, usually hydrogen peroxide or sodium percarbonate, is gentler and works at lower temperatures. It releases oxygen more slowly and does not produce chlorine gas. This makes it safer for colored fabrics. The remarkable aspect is that color is not a permanent property. It is a temporary arrangement of electrons. Change the arrangement and color disappears. Bleach rewrites the structure of molecules, erasing their ability to appear colored. Vinegar is dilute acetic acid, typically around 5% acid in water. It dissolves mineral deposits because many minerals are bases or carbonates. When acetic acid encounters calcium carbonate, the main component of limescale, a chemical reaction occurs. The acid donates hydrogen ions to the carbonate, forming carbonic acid. Carbonic acid is unstable and immediately breaks down into carbon dioxide gas and water. The calcium is left as calcium acetate, which dissolves in water. This reaction explains why vinegar removes limescale from kettles, showerheads, and faucets. The white crusty deposits are calcium carbonate left behind when hard water evaporates. Vinegar dissolves the deposits, turning them into soluble salts and releasing carbon dioxide bubbles. Vinegar also cuts through soap scum, which is a mixture of soap residue and minerals. The acid reacts with both components, breaking them down into substances that rinse away easily. It is effective on glass, tile, and stainless steel. However, vinegar should not be used on natural stone like marble or granite. These materials are made of calcium carbonate. Vinegar will etch and dull the surface by dissolving the stone itself. Similarly, vinegar can damage grout over time if used repeatedly. The beauty of vinegar as a cleaner is its simplicity. It is a weak acid, strong enough to dissolve minerals, but mild enough to be safe for most surfaces. The same chemistry that preserves pickles can also clean your kitchen. Ammonia is a small molecule, NH3, consisting of one nitrogen atom bonded to three hydrogen atoms. In water, ammonia acts as a weak base. It accepts hydrogen ions, forming ammonium ions and hydroxide ions. The hydroxide ions make the solution alkaline, which is useful for cutting through grease. Grease is nonpolar and does not dissolve in water. But in alkaline conditions, grease can undergo saponification. The hydroxide ions break down triglycerides into glycerol and fatty acid salts. Those fatty acid salts are water-soluble, so they rinse away. This is the same reaction that turns fat into soap, but in this case, it happens directly on the surface being cleaned. Ammonia is also volatile. It evaporates quickly, leaving no residue. This makes it popular for cleaning glass and mirrors. It dissolves grease smudges and dries rapidly, producing a streak-free finish. However, ammonia has a sharp, irritating odor. It can irritate eyes, skin, and respiratory passages. It should never be mixed with bleach. The two react to produce chloramine gases, which are toxic and can cause serious respiratory damage. The remarkable part is that a molecule as simple as ammonia can transform grease into something water-soluble. Alkalinity changes the rules. Substances that repel water suddenly dissolve, all because a base altered the chemical landscape. Baking soda, sodium bicarbonate, is mildly alkaline. It neutralizes both acids and weak bases, making it effective at removing odors. Many odors are caused by volatile acids, like butyric acid in rancid butter, or by volatile amines, which are weak bases. When baking soda contacts these molecules, it reacts with them to form neutral salts that are less volatile and less odorous. Baking soda also absorbs moisture. In a refrigerator or closet, it reduces humidity slightly, which can slow the growth of mold and bacteria that produce odors. The powder provides surface area for odor molecules to absorb, sticking to the surface of the crystals rather than floating in the air. The effect is subtle and works best in enclosed spaces. An open box of baking soda in a refrigerator gradually neutralizes odors over weeks. It does not eliminate them instantly, but it shifts the chemical balance toward neutrality and reduces the concentration of volatile compounds. Baking soda is also gentle. It is non-toxic and safe to use around food. It does not leave harmful residues or produce strong fumes. This makes it a versatile, mild option for odor control. The fascinating insight is that odor is molecular. smell is simply volatile chemicals reaching your nose. Baking soda changes those chemicals at the molecular level, neutralizing them into forms that do not trigger your scent receptors. Fabric softener contains quaternary ammonium compounds, also called quartz. These molecules have a positively charged nitrogen atom at one end and long hydrophobic tails at the other. When fabric softener is added during the rinse cycle, these molecules deposit onto the surface of fabric fibers. The positively charged heads bind to the negatively charged fibers. The long tails stick out into the air, forming a slippery coating. This coating has several effects. It reduces friction between fibers, making fabric feel softer and smoother. It reduces static cling because the coating prevents the buildup of static electricity. And it makes fibers less prone to tangling, which reduces wrinkles. Fabric softener also makes towels less absorbent. The hydrophobic coating repels water, which is why many people avoid using softener on towels and athletic wear. The same coating that makes fabric soft also prevents it from soaking up water effectively. Dryer sheets work on the same principle. They are coated with quartz that melt and transfer to fabrics during the heat of the dryer. The result is similar to liquid softener, just applied at a different stage. The striking part is that softness is not an inherent property of fabric. It is a coating applied after weaving. The molecules arrange themselves with precision, charged heads, binding to fibers and hydrophobic tails, creating a slippery surface. Chemistry makes scratchy cotton feel gentle. Dishwasher detergent is far more aggressive than hand soap. It contains strong alkalis like sodium carbonate or sodium hydroxide that would burn your skin. The high pH is necessary because dishwashers use relatively low temperatures and short cycles. The chemistry must work quickly. The alkali saponifies grease, breaking it into soluble salts. It also helps proteins denature and detach from surfaces. But alkalinity alone is not enough. Modern dishwasher detergents contain enzymes, biological catalysts that accelerate specific reactions. Proteases break down protein stains like egg and meat. Amylases break down starches. Lipases break down fats. Dishwasher detergent also contains builders, compounds that soften water by binding calcium and magnesium ions. Soft water allows surfactants to work more effectively. Without builders, minerals would interfere with cleaning and leave spots on dishes. Rinse Aid is a separate product that reduces surface tension. It helps water sheet off dishes rather than forming droplets. This prevents water spots, which are mineral deposits left behind when droplets evaporate. The remarkable part is how specialized the chemistry has become. Dishwasher detergent is not a simple soap. It is a mixture of alkalis, enzymes, builders, and surfactants, each serving a specific role. The formulation is calibrated for the machine, the water, and the types of soils commonly found on dishes. Oven cleaner is one of the harshest household chemicals. It typically contains sodium hydroxide, also known as lye, at concentrations high enough to cause chemical burns. Lye is a strong base, and it performs a dramatic transformation on baked-on grease. When lye contacts grease, it breaks triglycerides into glycerol and fatty acids through saponification. The fatty acids react with the lye to form soap. Essentially, oven cleaner turns grease into soap, which can then be wiped away. The reaction is fast and effective, cutting through carbonized residues that resist other cleaners. The process also generates heat. Saponification is exothermic, meaning it releases energy. This heat helps soften stubborn deposits, making them easier to remove. But it also makes oven cleaner dangerous. The combination of high pH heat and corrosive chemistry can damage skin, eyes, and respiratory tissues. Modern formulations sometimes use less aggressive alkalis or add gelling agents to reduce fumes and runoff. Some oven cleaners are designed to work over several hours at lower concentrations, trading speed for safety. The fascinating part is that lye does not dissolve grease in the usual sense. It chemically converts grease into a different substance, soap, that happens to be water-soluble. The same reaction that makes traditional bar soap also cleans ovens. Drain cleaners work through powerful chemical reactions. Most contain sodium hydroxide, lye, sometimes mixed with aluminum particles. When the mixture contacts water, several things happen. The lye dissolves in water, releasing heat. The aluminum reacts with the lye, producing hydrogen gas and more heat. The combination generates enough heat to melt grease and soap scum, clogging the drain. The heat also increases the effectiveness of the lye. Hot lye saponifies fats more rapidly than cold lye. The hydrogen gas bubbles provide mechanical agitation, helping to break apart clogs and push debris down the pipe. This chemistry is violent. The reaction can bring water to a boil in seconds. The gas produced can cause splashing. If the drain is completely blocked, pressure can build, leading to dangerous eruptions of caustic liquid. Enzymatic drain cleaners are safer but slower. They contain bacteria and enzymes that digest organic matter. These cleaners work over hours or days, breaking down hair, grease, and soap gradually. They are less effective on severe clogs, but much safer for pipes and users. The remarkable aspect is how much energy is released by simple reactions. Lye dissolving in water and aluminum, reacting with base produce heat, gas, and agitation, enough to clear blockages that resist mechanical plunging. Glass cleaners typically contain alcohol, surfactants, and water. The alcohol, usually isopropanol or ethanol, is the key ingredient. Alcohol is an excellent solvent for oils, fingerprints, and residues. It also evaporates quickly, which prevents streaks. Surfactants in the cleaner help lift dirt and spread the liquid evenly across the glass. They reduce surface tension, allowing the cleaner to sheet rather than bead. This promotes even drying and reduces the chance of water spots. Ammonia is sometimes included for its grease-cutting power, but it is optional. Alcohol alone is often sufficient for most glass cleaning tasks. Some formulations add vinegar or citric acid for additional cleaning power. especially against mineral deposits. The quick evaporation of alcohol is critical. Water-based cleaners can leave streaks because water evaporates slowly and unevenly, depositing minerals and residues as it dries. Alcohol evaporates rapidly and uniformly, leaving a clear, dry surface. The beauty of glass cleaners is simplicity. A volatile solvent mixed with a small amount of surfactant is all that is needed. The chemistry is straightforward, but the result is glass that looks invisible. Oxidizing cleaners use oxygen-based chemicals to break apart stain molecules. Common oxidizers include hydrogen peroxide and sodium percarbonate. When these compounds contact organic stains like wine, coffee, or blood, they donate oxygen atoms. The oxygen breaks chemical bonds in the chromophores, the parts of the molecule that absorb light and appear colored. Unlike chlorine bleach, oxygen bleaches are gentler. They do not produce harsh fumes or damage colors as readily. Hydrogen peroxide decomposes into water and oxygen, leaving no harmful residues. Sodium percarbonate dissolves in water to release hydrogen peroxide, providing a slow, sustained release of oxidizing power. Oxygen bleaches work best in warm or hot water. Heat accelerates the decomposition of peroxides, releasing oxygen more quickly. This is why oxygen-based laundry boosters are often used in hot wash cycles. The oxidation reaction is slower than chlorine bleach, but it is effective on a wide range of stains. It can remove color from organic molecules without destroying the fabric itself. The same chemistry that breaks apart stain molecules leaves cotton, polyester, and other fibers largely intact. The fascinating part is that oxygen, the element we breathe, is also a powerful chemical weapon against stains. In its reactive form, oxygen disassembles molecules, stripping away color one bond at a time. Enzyme cleaners harness biological catalysts to digest organic matter. Enzymes are proteins that speed up specific chemical reactions. Proteases break down proteins, turning them into amino acids. Amylases break down starches into sugars. Lipases break down fats into fatty acids and glycerol. Each enzyme is highly specific, working only on its target molecule. Laundry detergents often contain multiple enzymes. Proteases remove blood, grass, and food stains. Amylases remove starchy residues like pasta sauce or baby food. Lipases remove oily stains like salad dressing or body oils. Together, these enzymes digest a wide range of soils. Enzymes work best at warm temperatures, usually between 30 and 50 degrees Celsius. Too cool, and they work slowly. Too hot, and they denature, losing their catalytic shape. They also work best at moderate pH, neither too acidic nor too alkaline. The advantage of enzymes is specificity. They break down target molecules without harming fabrics. They are biodegradable and environmentally friendly. They work at lower temperatures than traditional detergents, saving energy. The remarkable insight is that life's chemistry can be borrowed for cleaning. The same enzymes that digest food in your stomach can digest stains on your clothes. Biology becomes technology. Plastics are polymers, long chains of repeating molecular units linked together. The word polymer comes from Greek roots meaning many parts. Each link in the chain is a monomer, a small molecule that can bond to others of its kind. When thousands or millions of monomers link together, they form a polymer with entirely new properties. Most plastics are made from petroleum. Oil is refined into simpler hydrocarbons like ethylene or propylene. These molecules contain carbon-carbon double bonds, which are reactive. Under the right conditions, heat, pressure, and catalysts, the double bonds break open and the molecules link together into chains. This process is called polymerization. The resulting material can be shaped by heat. Thermoplastics become soft and pliable when heated and rigid when cooled. This allows them to be molded, extruded, or formed into almost any shape. Once cooled, the polymer chains tangle together, creating a solid structure. The chains do not chemically bond to each other. They are held together by weaker forces, which is why thermoplastics can be melted and reshaped repeatedly. Different monomers produce different plastics. Polyethylene comes from ethylene. Polypropylene comes from propylene. Polystyrene comes from styrene. Each has distinct properties based on the structure of its monomer and the length of its chains. The fascinating part is that plastics are not truly solid. They are tangled masses of chains, more like cooked spaghetti than rigid crystals. Heat gives the chains enough energy to slide past one another. Cooling removes that energy, locking them in place again. Nylon was the first fully synthetic fiber, developed by Wallace Carothers at DuPont in the 1930s. It was created as an alternative to silk, which was expensive and difficult to obtain. Nylon is a polyamide, meaning its polymer chains are linked by amide bonds. These bonds form when an amine group reacts with a carboxylic acid, releasing water. The synthesis involves two monomers, a diamine and a dicarboxylic acid. When mixed, they react at their ends, linking into long chains. The chains align parallel to each other, forming strong, flexible fibers. Hydrogen bonds between chains give nylon its strength and resilience. Nylon can be drawn into thin filaments for stockings, woven into fabric for parachutes, or molded into gears and mechanical parts. Its versatility made it a revolutionary material. During World War II, nylon production was redirected entirely to military uses, parachutes, ropes, and tire cords, creating a shortage that became part of wartime culture. The discovery was not entirely planned. Carothers was investigating condensation polymers, materials formed by joining molecules and releasing small byproducts like water. Nylon emerged from systematic research, but its commercial success exceeded all expectations. The remarkable aspect is that nylon demonstrated chemistry could create materials that rivaled or surpassed natural ones. It was stronger than silk, more durable than cotton, and could be manufactured at scale. Synthetic did not mean inferior. It meant designed. Natural rubber is a polymer of isoprene, harvested as latex from rubber trees. In its raw form, rubber is soft and sticky. It becomes brittle in cold and melts in heat. Charles Goodyear discovered that adding sulfur and heating the mixture transformed rubber entirely. This process, called vulcanization, creates crosslinks between polymer chains. Sulfur atoms form bridges between chains at various points. These crosslinks prevent the chains from sliding past each other freely. The rubber becomes elastic. It can stretch when pulled because the chains uncoil and straighten. When released, the crosslinks pull the chains back into their tangled configuration. The rubber returns to its original shape. The number of crosslinks determines the rubber's properties. Light vulcanization with a small amount of sulfur produces soft, stretchy rubber for elastic bands and balloons. Heavy vulcanization with more sulfur produces hard rubber, once used for combs and bowling balls, now largely replaced by plastics. Synthetic rubbers are now more common than natural rubber. They are made from petroleum-derived monomers like styrene and butadiene. These synthetic versions can be tailored for specific properties, like resistance to oil, heat, or ozone. The beauty of vulcanization is that it turns a sticky, impractical material into something useful through simple chemistry. Cross-linking converts chaos into order. The chains remain free enough to move, but are tethered together, creating elasticity that recovers fully after stretching. Teflon is polytetrafluoroethylene, a polymer where every hydrogen atom in polyethylene is replaced with fluorine. Fluorine is the most electronegative element. It holds its electrons tightly, creating an extremely stable, inert surface. The carbon-fluorine bonds are among the strongest in chemistry. This structure makes Teflon extraordinarily slippery. Other molecules cannot bond to fluorine effectively. Water beads up and rolls off. Oil does not stick. Food slides across Teflon-coated pans without adhering. The coefficient of friction for Teflon is lower than almost any other solid material. Teflon also resists heat and chemical attack. It can withstand temperatures up to 260 degrees Celsius without degrading. Strong acids, bases, and solvents do not react with it. This makes it useful not only for cookware, but also for chemical processing equipment, gaskets, and insulation for wires. Teflon was discovered accidentally by Roy Plunkett at DuPont in 1938. He was investigating refrigerants when a pressurized canister of tetrafluoroethylene polymerized spontaneously. The white, waxy solid inside the canister had remarkable properties, and research quickly followed to understand and exploit them. The striking part is that replacing hydrogen with fluorine changes everything. The molecular change is simple, but the result is a material that resists nearly all chemical interactions. Teflon is chemistry's way of saying no to the rest of the molecular world. Kevlar is another polyamide like nylon, but its structure is radically different. The polymer chains contain aromatic rings, benzene-like structures that are flat and rigid. These rings align parallel to each other, forming sheets held together by hydrogen bonds. The sheets stack, creating a material with extraordinary tensile strength. Kevlar is 5 times stronger than steel by weight. When woven into fabric, it can stop bullets. The rigid aromatic rings prevent the chains from stretching or breaking under tension. Energy is distributed across the entire sheet rather than concentrated at a single point. Kevlar was invented by Stephanie Kwolek at DuPont in 1965. She was researching strong, lightweight fibers for tire reinforcement. The polymer solution she created was unexpectedly cloudy and thin, unlike the thick, clear solutions typical of other polymers. She convinced a reluctant technician to spin it into fiber, and the result was a material stronger than anything previously known. Kevlar is used in body armor, helmets, cut-resistant gloves, and cables. It resists heat and does not melt or drip. However, it degrades under ultraviolet light, so it must be protected from prolonged sun exposure. The fascinating part is that strength comes from rigidity and alignment. The chains cannot bend or slide. They are locked into a parallel configuration by hydrogen bonds. What makes Kevlar strong also makes it brittle. It cannot absorb impact by deforming. It either holds or breaks. Memory foam is a viscoelastic polymer, meaning it has properties of both viscous liquids and elastic solids. It was developed by NASA in the 1960s to improve seat cushioning for astronauts. The foam is made from polyurethane with added chemicals that increase its viscosity and density. At cool temperatures, memory foam is firm. The polymer chains are stiff and resist movement. When you press into it, the foam compresses slowly, then holds the shape of the impression. The chains take time to return to their original configuration. This is the viscous response. When warmed by body heat, the foam softens. The chains become more mobile, allowing the foam to contour around pressure points. This reduces pressure by distributing weight more evenly. Once pressure is removed, the foam slowly returns to its original shape over several seconds. The slow recovery is what distinguishes memory foam from ordinary foam. Regular foam compresses and rebounds almost instantly. Memory foam delays the rebound, creating a sensation of support that molds to the body. The chemistry involves cross-linked polymers with carefully controlled density and cell structure. The cells are open, allowing air to flow through and the foam to compress. The degree of cross-linking determines how quickly the foam recovers. The remarkable part is that the same material can be firm or soft depending on temperature. The polymer responds to heat by changing its viscosity, which changes how it feels and performs. Silly putty is a viscoelastic polymer made from silicone oil and boric acid. The boric acid cross-links the silicone chains loosely, creating a material that behaves differently depending on how force is applied. Pull it slowly, and it stretches like taffy. Pull it quickly, and it snaps. Roll it into a ball and drop it, and it bounces like rubber. Press it against newsprint, and it lifts ink from the page. This dual behavior comes from the time scale of deformation. When stretched slowly, the polymer chains have time to slide past each other. The crosslinks are temporary, breaking and reforming as the material flows. This is viscous behavior. When force is applied quickly, the chains do not have time to rearrange. The crosslinks hold, and the material behaves like an elastic solid. Silly putty was discovered accidentally during World War II by researchers trying to create synthetic rubber. It had no practical use at the time, but it became a popular toy. Later, astronauts used it to secure tools in zero gravity, and it found applications in physical therapy for strengthening hands. The striking aspect is that silly putty is neither solid nor liquid. It is both, depending on timing. The same substance flows like honey or bounces like rubber based solely on how fast you interact with it. Time becomes a variable in the material's identity. Superglue is cyanoacrylate, a monomer that polymerizes rapidly in the presence of water. Even the trace moisture on your skin or in the air is enough to trigger the reaction. When cyanoacrylate contacts water, it forms long polymer chains almost instantly. These chains bond tightly to the surfaces being joined, creating a strong, rigid adhesive. The polymerization is exothermic. It releases heat, which is why superglue can feel warm as it sets. The reaction is also very fast, often setting within seconds. This speed is both an advantage and a disadvantage. It bonds quickly, but it leaves no time to adjust positioning. Superglue was discovered by Harry Coover in 1942 while researching clear plastics for gun sights. Cyanoacrylates were rejected at the time because they stuck to everything. Years later, Coover realized that this property could be useful, and superglue was commercialized. Superglue bonds to a wide range of materials, including skin. It forms such strong bonds that it has been used in medical settings to close wounds. Veterinary and surgical formulations exist that are less irritating and more flexible than hardware store versions. The fascinating part is that superglue polymerizes without heat, pressure, or added catalysts. Water, the most common molecule on Earth, is the only trigger it needs. The adhesive carries its own reactivity, waiting patiently until moisture unlocks it. Polyvinyl chloride, or PVC, is one of the most widely used plastics. It is made by polymerizing vinyl chloride, a simple molecule with a carbon-carbon double bond and a chlorine atom. The resulting polymer is rigid and strong, used for pipes, window frames, and siding. Rigid PVC is hard and brittle, but when plasticizers are added, PVC becomes flexible. Plasticizers are small molecules that slip between polymer chains, increasing the space between them. This allows the chains to slide past each other more easily. The more plasticizer added, the more flexible the PVC becomes. Flexible PVC is used for cable insulation, inflatable structures, and synthetic leather. The plasticizers are not chemically bonded to the polymer. They are simply mixed in, which means they can leach out over time, especially when exposed to heat or solvents. This leaching has raised health and environmental concerns. The chemistry of plasticizers is about space. By forcing polymer chains apart, they reduce the forces holding the chains together. The material softens without changing the polymer itself. Remove the plasticizers and the PVC becomes rigid again. The remarkable insight is that rigidity and flexibility are not inherent. They are properties that can be adjusted by adding or removing small molecules. The same polymer can be a drain pipe or a raincoat, depending on what is mixed into it. Silicone polymers are based on silicon-oxygen backbones rather than carbon-carbon backbones like most plastics. Silicon and oxygen form very strong bonds, which gives silicones exceptional heat resistance and chemical stability. Silicones remain flexible at low temperatures and stable at high temperatures, far beyond what carbon-based polymers can tolerate. Silicone molecules also have organic side groups, usually methyl groups, attached to the silicon atoms. These side groups make silicones hydrophobic and give them a slippery texture. Silicones do not stick to most materials, which makes them useful as molds, sealants, and lubricants. Silicone can be formulated as oils, gels, rubbers, or resins, depending on the degree of cross-linking. Lightly cross-linked silicones are soft and gel-like. Heavily cross-linked silicones are hard and resin-like. The versatility allows silicones to be tailored for specific applications. Silicone rubber remains elastic at temperatures from -55 to 300 degrees Celsius. It does not degrade in sunlight or ozone. It is chemically inert and biocompatible, which is why it is used in medical implants and kitchen utensils. The beauty of silicone chemistry is that it replaces carbon with silicon, creating a polymer family with radically different properties. Silicon-oxygen bonds are stronger and more stable than carbon-carbon bonds, and that stability makes silicones perform where other polymers fail. Biodegradable plastics are designed to break down under environmental conditions. They contain chemical bonds that microbes can recognize and cleave. Traditional plastics like polyethylene are made of carbon-carbon bonds, which are strong and stable. Microbes have few enzymes capable of breaking them down, so these plastics persist for decades or centuries. Biodegradable plastics use different chemistries. Polylactic acid, or PLA, is made from fermented plant sugars. Its backbone contains ester bonds, which microbes can hydrolyze into lactic acid. Lactic acid is a natural compound that microbes metabolize easily. PLA degrades in industrial composting facilities where heat, moisture, and microbes are abundant. Polyhydroxyalkanoates, or PHAs, are made by bacteria as energy storage molecules. They are truly biodegradable, breaking down in soil, water, and marine environments. However, they are more expensive to produce than conventional plastics. The challenge is balancing durability and degradability. Plastics must be stable during use, but break down quickly after disposal. Achieving this requires careful design of the polymer's chemical structure and the conditions under which it will degrade. The fascinating part is that biodegradability is molecular. It depends on whether enzymes exist that can grip the polymer chain and break its bonds. Small changes in structure determine whether a plastic lasts forever or disappears in months. Aerogel is one of the lightest solid materials ever made. It is a gel where the liquid has been replaced with gas. The solid structure is a network of silica particles bonded together, creating a porous scaffold. The pores are filled with air, which makes up 99% or more of the aerogel's volume. Aerogel is made by creating a wet gel, usually from silicon alkoxides dissolved in alcohol. The gel forms a network as the molecules link together. Then the liquid is removed using supercritical drying, a process where temperature and pressure are raised until the liquid becomes a supercritical fluid. In this state, there is no surface tension, so the liquid evaporates without collapsing the delicate gel network. The result is an incredibly light material. Some aerogels are less dense than air. They are excellent insulators because air trapped in tiny pores cannot convect heat. They are also transparent or translucent, giving them a ghostly, ethereal appearance. Aerogel is used in insulation, particularly in aerospace applications where weight is critical. It has been used on Mars rovers to insulate electronics from extreme cold. It is also used in particle detectors because its low density minimizes interference with high-energy particles. The wonder is that aerogel is mostly nothing. Its structure is air held in place by a whisper of silica. It is the lightest way to build a solid. Iron rusts when exposed to oxygen and water. Rust is iron oxide, specifically hydrated iron oxide. The process is electrochemical. Iron atoms lose electrons, becoming iron ions. Those electrons are transferred to oxygen, which combines with water to form hydroxide ions. The iron ions and hydroxide ions react to form iron oxide, which precipitates as the reddish-brown flakes we call rust. Rust is porous. It does not protect the underlying metal. Water and oxygen penetrate through it, allowing the corrosion to continue deeper into the iron. Over time, rust can weaken structures, making them brittle and unsafe. Rust requires both oxygen and water. In dry air, iron does not rust. Underwater, in the absence of dissolved oxygen, rusting is slow. But in moist air, where both are present, rusting proceeds rapidly. Salt accelerates the process by increasing the conductivity of water, allowing electrons to move more easily. Preventing rust involves blocking oxygen, water, or both. Paint creates a barrier. Oil repels water. Galvanizing coats iron with zinc, which corrodes instead of the iron. Stainless steel adds chromium, which forms a protective oxide layer. The fascinating part is that rust is not decay in the organic sense. It is a chemical transformation where iron returns to an oxide form, similar to the ore it was originally smelted from. Rust is iron trying to go home. Stainless steel resists rust because it contains chromium, at least 10.5% by weight. Chromium reacts with oxygen more readily than iron does. When stainless steel is exposed to air, a thin layer of chromium oxide forms on the surface almost instantly. This layer is only a few atoms thick, but it is dense and impermeable. The chromium oxide layer prevents oxygen and moisture from reaching the iron beneath. Unlike rust, chromium oxide adheres tightly to the metal. It does not flake off. If the surface is scratched, exposing fresh metal, chromium in the alloy reacts with oxygen to repair the protective layer automatically. This self-healing property makes stainless steel remarkably durable. It can be used in wet, corrosive environments without degrading. Different grades of stainless steel contain different amounts of chromium and other elements like nickel and molybdenum, which further enhance corrosion resistance. Stainless steel is not completely immune to corrosion. In chloride-rich environments like seawater or under conditions where the oxide layer cannot form, stainless steel can still corrode. But under normal conditions, the chromium oxide layer provides excellent protection. The remarkable insight is that corrosion resistance comes from controlled oxidation. Stainless steel rusts instantly, but the rust is chromium oxide, and that rust protects rather than destroys. Aluminum oxidizes as soon as it contacts air. A freshly cut piece of aluminum reacts with oxygen within seconds, forming a thin layer of aluminum oxide on the surface. This oxide layer is extremely stable and adheres tightly to the metal. It is only a few nanometers thick, but it effectively stops further oxidation. Aluminum oxide is hard and chemically inert. It does not flake off like rust. It does not dissolve in water. It protects the underlying aluminum so effectively that the metal appears not to corrode at all. In reality, aluminum corrodes immediately and completely, but the corrosion product is protective. Anodizing is a process that thickens the oxide layer artificially. Aluminum is submerged in an acid bath, and an electric current is applied. This forces rapid oxidation, building up a thicker oxide coating. Anodized aluminum is harder and more resistant to wear. Dyes can be added before sealing the coating, producing colored aluminum. The oxide layer can be damaged by strong alkalis, which dissolve aluminum oxide. This is why aluminum should not be cleaned with lye-based oven cleaners or left in contact with concrete, which is alkaline. The beauty is that aluminum defeats corrosion through speed. It oxidizes so fast that oxygen never reaches deeper layers. The metal is covered in its own decay, and that decay becomes armor. Galvanization protects iron by coating it with zinc. Zinc is more reactive than iron. When exposed to corrosive conditions, zinc oxidizes preferentially, leaving the iron untouched. This is called sacrificial protection. The zinc sacrifices itself to protect the iron. Even if the coating is scratched, exposing the iron beneath, the zinc continues to protect. Zinc corrodes at the scratch site, and the electrons released flow to the iron, preventing it from oxidizing. The iron remains protected as long as zinc is present nearby. Zinc oxide, the product of zinc corrosion, is less porous than rust. It forms a protective layer that slows further corrosion. This means zinc-coated steel corrodes much more slowly than bare steel, even after the coating is damaged. Galvanized steel is used for roofing, fencing, and outdoor structures. The zinc coating can last for decades in normal conditions. Eventually, the zinc is consumed and the underlying steel begins to rust. But galvanization buys time, often many years. The striking part is that protection comes from vulnerability. Zinc corrodes easily, and that ease of corrosion is exactly what protects the iron. Reactivity becomes a shield. Copper turns green when exposed to air and moisture over time. This green coating is called patina. It forms through a series of oxidation reactions. Initially, copper reacts with oxygen to form copper oxide, which is black or brown. Over time, copper oxide reacts with carbon dioxide and water in the air to form copper carbonate. In coastal areas where sulfur compounds are present, copper sulfate also forms. These compounds create the distinctive blue-green patina seen on old copper, roofs, and statues. The patina is not merely discoloration, it is a protective layer. Unlike rust on iron, patina adheres tightly to the copper surface and prevents further corrosion. The underlying copper remains intact. This is why copper roofing can last for centuries. The patina thickens slowly over decades, eventually forming a stable coating that requires no maintenance. The Statue of Liberty is covered in copper sheets that have developed a thick green patina over more than a century. The patina has become iconic, but the copper beneath remains structurally sound. Removing the patina would expose fresh copper to renewed corrosion, so it is left in place. Patina can be created artificially by exposing copper to acids, salts, or sulfur compounds. Artists and craftspeople use these techniques to produce decorative finishes on copper sculptures and jewelry. Each combination of chemicals produces a different shade of green or blue. The beauty of patina is that it transforms over time. Bright, shiny copper slowly becomes muted and green. The change is gradual and irreversible under normal conditions. Copper wears its age visibly, and that weathered appearance has aesthetic value. Gold does not tarnish, it does not oxidize, it does not corrode. Gold is one of the least reactive elements. Its electrons are held so tightly that other atoms cannot pull them away. This chemical inertness is why gold has been valued throughout history. It does not degrade. It remains bright and lustrous indefinitely. Gold's lack of reactivity comes from relativistic effects. Gold atoms are heavy, with 79 protons in the nucleus. The innermost electrons orbit at speeds approaching the speed of light. Relativity causes their orbits to contract slightly. This changes the energy levels of the outer electrons, making them less available for bonding. As a result, gold resists forming compounds. Gold does dissolve in aqua regia, a mixture of nitric acid and hydrochloric acid. The acids work together to oxidize gold and form soluble gold chloride. This property was historically used to test gold purity. Genuine gold resists most acids, but dissolves in aqua regia. Gold's unreactivity makes it ideal for electronics. Gold-plated contacts do not corrode, ensuring reliable electrical connections over time. It is also biocompatible, which is why gold is used in dental work and medical implants. The body does not react to gold. It remains inert and stable. The wonder at gold's beauty is chemical. Its color and shine are not coatings or treatments. They are intrinsic properties that persist because the metal refuses to react with the world around it. Silver tarnishes when exposed to sulfur compounds in the air. The tarnish is silver sulfide, a black compound that forms a thin film on the surface. Even tiny amounts of hydrogen sulfide, released by decaying organic matter, eggs, or rubber, can tarnish silver rapidly. Unlike patina on copper, silver sulfide is generally considered undesirable. It obscures the metal's bright, reflective surface. Polishing removes the tarnish by mechanically wearing away the silver sulfide layer, but it also removes a tiny amount of silver. Frequent polishing gradually wears down silver objects. Chemical tarnish removal works differently. Aluminum foil in a baking soda solution can reverse tarnish. The aluminum acts as a reducing agent, donating electrons to the silver sulfide. This converts silver sulfide back into metallic silver. The sulfur transfers to the aluminum, forming aluminum sulfide. The silver is restored without removing any metal. Silver tarnishes more quickly in humid conditions and in the presence of sulfur-containing foods like onions and eggs. Storing silver in anti-tarnish cloth or airtight containers slows the process by limiting exposure to sulfur compounds. The striking part is that tarnish is reversible. Silver sulfide can be converted back to silver through chemistry. The same cannot be said for rust, which represents a more complete transformation. Silver's tarnish is a temporary disguise, not permanent damage. Bronze is an alloy of copper and tin, typically around 88% copper and 12% tin. Bronze is harder and stronger than pure copper. This happens because tin atoms are larger than copper atoms. When mixed into the copper crystal structure, tin atoms disrupt the orderly arrangement. They create irregularities that prevent layers of atoms from sliding past each other easily. In pure copper, atoms are arranged in layers that can slip when force is applied. This makes copper soft and easily deformed. Adding tin creates obstacles within those layers. Dislocations, the defects that allow slipping, cannot move as freely. The alloy resists deformation, making it harder. Bronze was one of the first alloys humans created, giving its name to an entire age of prehistory. Bronze tools and weapons were superior to copper ones because they held edges better and did not bend as easily. Bronze also has a lower melting point than copper, making it easier to cast into complex shapes. Different ratios of copper and tin produce different properties. More tin makes bronze harder, but also more brittle. Less tin produces a softer, more ductile alloy. Ancient metalworkers learned these relationships through experimentation, adjusting composition for specific uses. The remarkable insight is that hardness comes from imperfection. Pure copper is too orderly, too regular. Bronze gains strength by introducing disorder at the atomic level. Mixing improves performance. Steel is iron with a small amount of carbon, typically less than 2% by weight. Carbon atoms are much smaller than iron atoms. When carbon dissolves in iron, the carbon atoms fit into the spaces between iron atoms. These interstitial carbon atoms distort the crystal lattice, making it harder for layers of iron atoms to slide past each other. The amount of carbon determines the steel's properties. Low carbon steel, around 0.05 to 0.25% carbon, is soft and ductile. It can be bent and formed easily, making it useful for car bodies and construction. Medium carbon steel, around 0.25 to 0.6% carbon, is stronger and used for gears, axles, and rails. High carbon steel, around 0.6 to 1.5% carbon, is very hard and holds a sharp edge, making it ideal for knives and cutting tools. Heat treatment further alters steel's properties. Heating steel allows carbon atoms to redistribute. Rapid cooling, called quenching, traps the carbon in a distorted crystal structure called martensite. Martensite is extremely hard but brittle. Tempering, reheating to a moderate temperature, relieves some of the stress and increases toughness without sacrificing too much hardness. Steel represents humanity's mastery of carbon chemistry. Adjusting carbon content and thermal processing produces materials with vastly different behaviors. The same elements, iron and carbon, become soft and formable or hard and sharp, depending on how they are combined. Electroplating uses electricity to deposit a thin layer of metal onto a surface. The object to be plated is submerged in a solution containing ions of the plating metal. The object is connected to the negative terminal of a power supply, making it the cathode. A piece of the plating metal is connected to the positive terminal, making it the anode. When current flows, metal ions in the solution are attracted to the cathode. They gain electrons and are reduced to metallic form, depositing onto the surface. At the anode, metal atoms lose electrons and dissolve into the solution as ions, replenishing the supply. The process continues as long as current flows, building up a layer atom by atom. Electroplating is used to coat objects with gold, silver, nickel, chromium, or other metals. Chrome plating provides a shiny, corrosion-resistant finish. Gold plating makes inexpensive jewelry appear valuable. Nickel plating protects steel from rust. The thickness of the plating depends on current, time, and the concentration of metal ions in the solution. Thicker coatings provide better protection but cost more. Very thin coatings, just microns thick, are common in decorative applications. The beauty of electroplating is precision. Electricity controls deposition atom by atom. The process is uniform and reproducible. It transforms surfaces without changing the underlying material, adding properties that the base metal lacks. The sky appears blue because of the way air molecules scatter sunlight. Sunlight contains all colors of the visible spectrum. When sunlight enters the atmosphere, it collides with nitrogen and oxygen molecules. These molecules are much smaller than the wavelength of light. Small particles scatter short wavelengths more effectively than long wavelengths. Blue and violet light have short wavelengths. They scatter in all directions as they pass through air. Red and orange light have longer wavelengths. They pass through air with less scattering. This phenomenon is called Rayleigh scattering. When you look at the sky, you see scattered blue light coming from all directions. The sky appears blue because blue wavelengths are scattered most intensely. Violet light is scattered even more than blue, but our eyes are less sensitive to violet, and much of it is absorbed by the upper atmosphere. So we perceive the sky as blue rather than violet. Near the horizon, the sky appears paler. Light travels through more atmosphere to reach your eyes when looking toward the horizon. The increased scattering makes the blue less saturated, shifting toward white. On the moon, the sky is black even during the day. There is no atmosphere to scatter light. You see only the direct light from the sun and stars against the blackness of space. The wonder is that blue sky is not a property of air. It is a consequence of scattering. Air itself is colorless. The color emerges from the interaction between light and molecules. Sunsets are red for the same reason the sky is blue, but the effect is more extreme. At sunset, sunlight passes through a much thicker layer of atmosphere before reaching your eyes. It travels horizontally through the atmosphere rather than vertically downward. Blue and violet light scatter out of the beam during this long journey. By the time sunlight reaches you, most of the short wavelengths are gone. Only red, orange, and yellow wavelengths remain. These long wavelengths scatter less and penetrate the atmosphere more effectively. The more atmosphere the light travels through, the redder the sunset. Dust, pollution, and water droplets in the air enhance the effect. They scatter even more blue light, leaving the reds and oranges purer. This is why sunsets can be especially vivid after volcanic eruptions, when the stratosphere contains elevated levels of aerosol particles. The same principle explains why the sun appears yellow during the day and orange or red near the horizon. High in the sky, the sun's light travels through less atmosphere. Some blue is scattered away, but much remains, giving the sun a white or pale yellow appearance. Near the horizon, the blue is almost completely removed, and the sun appears orange or red. The remarkable part is that the sun itself does not change color. It emits the same spectrum of light at all times. Color is an artifact of the path light takes through the atmosphere. Ozone forms in the stratosphere through a process driven by ultraviolet radiation. Oxygen normally exists as O2. Two oxygen atoms bonded together. When high-energy UV light strikes an O2 molecule, it splits the molecule into two individual oxygen atoms. These free oxygen atoms are highly reactive. When a free oxygen atom collides with an O2 molecule, they combine to form ozone, O3. Ozone is unstable. It absorbs UV radiation and breaks apart into O2 and a free oxygen atom. The free atom can recombine with another O2 to form ozone again. This cycle continues, with ozone constantly forming and breaking down. In the process, UV radiation is absorbed and converted into heat. This absorption protects life on Earth. UV radiation damages DNA and can cause skin cancer and other health problems. The ozone layer acts as a shield, filtering out much of the most harmful UV before it reaches the surface. Chlorofluorocarbons, or CFCs, once used in refrigerators and aerosol cans, destroy ozone. In the stratosphere, UV light breaks apart CFC molecules, releasing chlorine atoms. A single chlorine atom can destroy thousands of ozone molecules before it is removed from the stratosphere. This led to the formation of the ozone hole over Antarctica. The Montreal Protocol, an international agreement, phased out CFC production. Ozone levels have begun to recover slowly. The chemistry that protects us from UV radiation is now being protected by international cooperation. Greenhouse gases trap heat by absorbing infrared radiation. Sunlight passes through the atmosphere and warms the Earth's surface. The surface emits heat as infrared radiation. Some of this infrared escapes into space, but some is absorbed by greenhouse gases like carbon dioxide, methane, and water vapor. These molecules absorb infrared because they have the right molecular structure. When infrared light strikes a greenhouse gas molecule, it causes the molecule to vibrate. The molecule absorbs the energy and then re-emits it in all directions, including back toward the Earth's surface. This process traps heat in the atmosphere, warming the planet. Not all molecules absorb infrared. Nitrogen and oxygen, which make up most of the atmosphere, do not. They lack the necessary molecular vibrations. Carbon dioxide and methane, though present in much smaller amounts, are effective absorbers. Water vapor is the most abundant greenhouse gas and a powerful absorber, but its concentration varies widely. Human activities have increased the concentration of carbon dioxide through burning fossil fuels. More carbon dioxide means more infrared absorption, which means more heat trapped in the atmosphere. This is the mechanism behind climate warming. The chemistry is straightforward. Molecules absorb light at specific wavelengths. The wavelengths they absorb depend on their vibrational modes. Carbon dioxide happens to absorb strongly in the infrared range, the exact range Earth emits. This overlap is not coincidence. It is molecular resonance. Smog forms when nitrogen oxides and hydrocarbons react in the presence of sunlight. Cars and industrial processes release nitrogen oxides. Molecules like NO and NO2, along with volatile organic compounds from gasoline and solvents. In still air, these pollutants accumulate. Sunlight provides energy to drive chemical reactions. UV light breaks apart nitrogen dioxide into nitrogen monoxide and a free oxygen atom. The oxygen atom reacts with oxygen molecules to form ozone. Ozone then reacts with hydrocarbons, producing a complex mixture of oxidized compounds, including aldehydes, ketones, and peroxyacyl nitrates. These compounds irritate eyes and lungs. The reactions proceed in a cycle. Nitrogen oxides and hydrocarbons are consumed but also regenerated, allowing the smog to persist and intensify throughout the day. By afternoon, ozone concentrations can reach levels that trigger health warnings. Weather conditions influence smog formation. Temperature inversions, where warm air traps cooler air near the ground, prevent pollutants from dispersing. Sunlight intensity affects reaction rates. Cities with heavy traffic, abundant sunlight, and frequent inversions, like Los Angeles, experience chronic smog problems. The chemistry of smog is photochemistry. Light is not just illumination, it is a reactant. Photons break bonds and initiate reactions that would not occur in the dark. Smog is proof that light can be a pollutant's ally. Acid rain occurs when sulfur dioxide and nitrogen oxides dissolve in atmospheric moisture. These gases are released by burning coal, oil, and gas, particularly in power plants and vehicles. Once in the atmosphere, sulfur dioxide reacts with water vapor to form sulfuric acid. Nitrogen oxides react to form nitric acid. These acids dissolve in cloud droplets and fall as rain, snow, or fog. Normal rain is slightly acidic, with a pH around 5.6 because carbon dioxide dissolves in water to form weak carbonic acid. Acid rain has a pH below 5, sometimes as low as 3, which is roughly as acidic as vinegar. This acidity damages forests by leaching nutrients from soil and releasing toxic aluminum. It acidifies lakes and streams, harming fish and aquatic life. It corrodes buildings and statues, particularly those made of limestone or marble, which are calcium carbonate. Acid deposition can occur far from pollution sources. Winds carry the gases hundreds of miles before they dissolve in rain. Scandinavian countries experienced severe acid rain from pollution originating in the United Kingdom and Central Europe. Reducing sulfur emissions has improved acid rain in many regions. Scrubbers in power plants remove sulfur dioxide before it reaches the atmosphere. Catalytic converters in vehicles reduce nitrogen oxide emissions. These interventions demonstrate that atmospheric chemistry can be influenced by controlling emissions at the source. Lightning converts nitrogen gas into nitrates that fertilize soil. Nitrogen makes up 78% of the atmosphere, but it exists as N2, a molecule with a very strong triple bond. Most organisms cannot break this bond. They cannot use atmospheric nitrogen directly. Lightning provides enough energy to split nitrogen molecules. The intense heat, around 30,000 degrees Celsius, breaks the N2 bond. The freed nitrogen atoms react with oxygen to form nitrogen oxides. These oxides dissolve in rain, forming nitrates. Nitrates fall to the ground, where plants absorb them through their roots. This natural nitrogen fixation was crucial before the development of synthetic fertilizers. Lightning produces an estimated 5 to 8 million tons of nitrogen compounds annually. While this is small compared to industrial nitrogen fixation today, it was the primary source of usable nitrogen for ecosystems before agriculture. The Haber-Bosch process, developed in the early 20th century, mimics lightning's effect. It uses high temperature and pressure, along with a catalyst, to convert nitrogen and hydrogen into ammonia. Ammonia is then converted into fertilizers. This industrial process now supplies most of the nitrogen used in agriculture, feeding billions of people. The fascinating part is that lightning performs chemistry that requires industrial conditions to replicate. A bolt of electricity does in a microsecond what chemists need: reactors, catalysts, and energy to achieve. Clouds form when water vapor condenses around aerosol particles. The air always contains tiny particles: dust, pollen, sea salt, and pollution. These particles are hygroscopic, meaning they attract water. When humid air cools, water vapor begins condensing onto these particles, forming microscopic droplets. Without aerosol particles, water vapor would require much cooler temperatures to condense. The particles provide surfaces where water molecules can cluster and bond. Once a droplet forms, more water vapor condenses onto it, and the droplet grows. Millions of these droplets together form a cloud. The size and number of aerosol particles affect cloud properties. Many small particles produce clouds with many small droplets. These clouds are bright and reflect sunlight effectively. Fewer, larger particles produce clouds with fewer, larger droplets. These clouds are darker and more likely to produce rain. Pollution can alter cloud formation. Smoke and industrial emissions release aerosols that increase droplet counts. This changes how clouds reflect light and how quickly they produce precipitation. The interactions between aerosols and clouds are complex and remain an active area of research in climate science. The wonder is that clouds are not just water. They are water organized around dust. The invisible particles in the air become the seeds of visible clouds. The ocean absorbs carbon dioxide from the atmosphere. When CO2 dissolves in seawater, it reacts with water to form carbonic acid. Carbonic acid is weak, but it lowers the pH of seawater slightly. This process is called ocean acidification. As atmospheric CO2 concentrations rise, more CO2 dissolves in the ocean and pH drops further. Lower pH affects marine organisms that build shells and skeletons from calcium carbonate. Carbonic acid shifts the carbonate equilibrium, reducing the availability of carbonate ions. This makes it harder for corals, shellfish, and plankton to form calcium carbonate structures. Some organisms must expend more energy to build shells. Others experience shell thinning or dissolution. The ocean has absorbed about a third of the carbon dioxide released by human activities. This has buffered atmospheric warming, but at the cost of changing ocean chemistry. The pH of surface seawater has dropped by about 0.1 units since the Industrial Revolution, representing a 30% increase in acidity. The chemistry is straightforward. Carbon dioxide plus water equals carbonic acid. But the consequences ripple through ecosystems. Shell forming organisms are foundational to marine food webs. Changes at the chemical level affect biology at every scale. Chlorofluorocarbons destroy ozone by releasing chlorine radicals. CFCs are stable compounds made of carbon, chlorine, and fluorine. They were widely used in refrigerators, air conditioners, and aerosol sprays because they are non-toxic and non-flammable. However, their stability means they persist in the atmosphere for decades. CFCs eventually drift into the stratosphere. There, intense UV radiation breaks the carbon-chlorine bonds, releasing free chlorine atoms. A chlorine atom reacts with an ozone molecule, forming chlorine monoxide and oxygen. Chlorine monoxide then reacts with another ozone molecule, releasing O2 and regenerating the free chlorine atom. The chlorine is not consumed. It acts as a catalyst, destroying ozone repeatedly. A single chlorine atom can destroy tens of thousands of ozone molecules before it is finally removed from the stratosphere. This catalytic destruction led to the formation of the ozone hole over Antarctica, where conditions favor the chemistry. The discovery of ozone depletion led to the Montreal Protocol in 1987, which phased out CFC production worldwide. This remains one of the most successful international environmental agreements. Ozone levels are slowly recovering, though full recovery will take decades. The striking lesson is that chemical stability is not always desirable. CFCs were chosen because they do not react, but that stability allowed them to reach the stratosphere, where they finally did react, with devastating consequences. Chlorophyll captures sunlight by absorbing red and blue wavelengths. The molecule has a flat ring structure with a magnesium atom at its center. This ring, called a porphyrin, has alternating single and double bonds that allow electrons to move freely across the structure. When light strikes chlorophyll, electrons absorb energy and jump to higher energy levels. Red light around 660 nanometers and blue light around 430 nanometers have exactly the right energy to excite chlorophyll electrons. Green light around 550 nanometers does not match chlorophyll's energy requirements. It is reflected rather than absorbed, which is why plants appear green. We see the color chlorophyll rejects. The absorbed energy drives photosynthesis. Excited electrons are passed to other molecules in a chain of reactions that ultimately convert carbon dioxide and water into glucose. The energy from sunlight is stored in the chemical bonds of sugar. Different forms of chlorophyll exist. Chlorophyll A is the primary photosynthetic pigment in all plants. Chlorophyll B absorbs slightly different wavelengths and passes energy to chlorophyll A. Together, they capture a broader spectrum of light than either could alone. Plants appear to waste green light, but this may be adaptive. Intense sunlight can damage photosynthetic machinery. Reflecting green light may protect plants from absorbing too much energy. Evolution optimized for survival, not efficiency. Photosynthesis splits water molecules to release oxygen as waste. Water is one of the most stable molecules, yet plants break it apart billions of times per second. This happens at a protein complex called photosystem II, which contains a cluster of 4 manganese atoms and 1 calcium atom. When chlorophyll absorbs light, it ejects an electron. That electron must be replaced. The manganese cluster pulls electrons from water molecules. Each water molecule, H2O, loses 2 electrons and splits into oxygen and hydrogen ions. 2 water molecules yield 1 oxygen molecule, 4 hydrogen ions, and 4 electrons. The oxygen is released into the atmosphere. It is a byproduct, not the goal. Plants evolved photosynthesis to make food, not oxygen. Yet this waste product transformed Earth. For billions of years, oxygen was rare. Photosynthetic organisms gradually filled the atmosphere with oxygen, enabling the evolution of animals that breathe. The manganese cluster is exquisitely tuned. Extracting electrons from water requires immense energy. Because the oxygen-hydrogen bond is strong, the cluster accumulates energy from 4 separate photons before it can break water. This 4-step mechanism prevents wasteful side reactions. Every breath you take originates in this chemistry. Oxygen in your lungs was once bound to hydrogen in water. A plant used sunlight to break that bond, and the oxygen drifted free. Autumn leaves change color when chlorophyll breaks down. Throughout spring and summer, chlorophyll dominates. Its green color masks other pigments present in the leaf. As days shorten and temperatures cool, trees begin preparing for winter. They stop producing chlorophyll and start breaking down what remains, salvaging valuable nitrogen from the molecule. Without green chlorophyll, other pigments become visible. Carotenoids, which were always present, now show their yellow and orange hues. Carotenoids are long hydrocarbon chains with alternating double bonds. They absorb blue and green light and reflect yellow, orange, and red. Carrots, corn, and bananas owe their colors to carotenoids. Anthocyanins produce red and purple colors. Unlike carotenoids, anthocyanins are synthesized in autumn in response to bright light and cool temperatures. Sugars trapped in the leaf react with proteins to form these pigments. Their function is debated. They may protect the leaf from light damage during the breakdown process, or they may deter insects from laying eggs on the senescing tree. Not all trees produce vivid autumn colors. The intensity depends on weather. Warm, sunny days and cool but not freezing nights produce the brightest displays. Drought or early frost can cause leaves to drop before colors develop fully. Leaves do not change color. They reveal color that was hidden. The transformation is subtraction, not addition. Caffeine evolved in plants as a natural insecticide. Coffee, tea, and cacao plants produce caffeine in their leaves, seeds, and fruits. Insects that feed on caffeine-containing plants experience disrupted nervous systems. High doses are toxic. Caffeine protects the plant from herbivores. But caffeine has another role. It acts as a reward for pollinators. Nectar in some flowers contains low doses of caffeine. Bees that drink caffeinated nectar remember the flower more vividly. Caffeine enhances memory formation in bee brains, making them more likely to return. The plant manipulates pollinator behavior through chemistry. In humans, caffeine blocks adenosine receptors in the brain. Adenosine accumulates throughout the day, promoting sleepiness. Caffeine molecules are shaped similarly to adenosine and fit into the same receptors without activating them. This prevents adenosine from binding, delaying the onset of fatigue. Caffeine also increases dopamine signaling, which improves mood and concentration. The effects peak about 30 to 60 minutes after consumption and can last several hours, depending on individual metabolism. Plants invented caffeine to kill insects and recruit pollinators. Humans discovered it and built entire cultures around its consumption. A molecule meant as poison became one of the world's most popular drugs. Capsaicin in peppers triggers pain receptors to deter mammals. Birds are immune to capsaicin. They eat hot peppers without discomfort and disperse the seeds widely. Mammals, on the other hand, experience intense burning. Capsaicin binds to receptors that normally detect heat and physical damage. The receptors send pain signals to the brain, even though no actual harm occurs. Pepper plants evolved capsaicin to exploit this difference. Birds, with their ability to fly long distances, are ideal seed dispersers. Mammals, which tend to chew seeds and destroy them, are poor dispersers. By making the fruit painful to mammals but not to birds, peppers ensure their seeds are spread by the right animals. Capsaicin does not damage tissue at the concentrations found in food. It creates the sensation of burning without actual burns. The pain is real, but it is a false alarm. Repeated exposure can desensitize receptors temporarily, which is why people who eat spicy food regularly build tolerance. Humans are unusual in seeking out capsaicin despite the pain. Some researchers suggest we enjoy the thrill of a safe danger, triggering pain responses while knowing we are not in real peril. Others point to endorphin release following capsaicin exposure, creating a mild high. Peppers did not intend for humans to enjoy them. We are an accident, a species that embraced what was meant to repel. Mint feels cool because menthol activates cold-sensing proteins. Temperature receptors in your skin and mouth detect changes in heat. One receptor, called TRPM8, opens when temperatures drop below about 26 degrees Celsius. When it opens, ions flow through, and your nervous system interprets this as coldness. Menthol binds to TRPM8 and forces it to open even at normal temperatures. The receptor signals cold, and you perceive a cooling sensation. No temperature change occurs. The cooling is entirely perceptual, a trick of molecular mimicry. Menthol is a terpene, a class of molecules built from 5-carbon isoprene units. Many plants produce terpenes for defense or communication. Menthol specifically is found in mint plants, where it may deter herbivores or inhibit competing plants. The cooling effect explains menthol's use in products like toothpaste, cough drops, and topical pain relievers. The sensation can distract from pain or irritation. It also stimulates saliva production and creates a perception of freshness. Capsaicin and menthol are opposites in effect, but similar in mechanism. Both bind to temperature receptors. Capsaicin activates heat sensors. Menthol activates cold sensors. Neither changes actual temperature. Both hijack perception by speaking the language of temperature receptors. Aspirin comes from salicylic acid found naturally in willow bark. For thousands of years, people chewed willow bark to relieve pain and fever. The active compound, salicylic acid, inhibits enzymes that produce inflammatory signaling molecules called prostaglandins. Fewer prostaglandins mean less pain, fever, and inflammation. Salicylic acid works, but it irritates the stomach. In the late 1800s, chemists at Bayer modified the molecule, adding an acetyl group. This created acetyl salicylic acid or aspirin. Aspirin is less irritating because the acetyl group masks the acidic portion of the molecule. Once absorbed, the body removes the acetyl group, converting aspirin back into salicylic acid. Aspirin does more than relieve pain. It prevents blood clots by inhibiting platelet aggregation. This makes it useful for preventing heart attacks and strokes. A single aspirin can reduce clotting for days because it permanently modifies the enzyme it targets. The discovery of aspirin demonstrated that natural compounds could be improved through chemical modification. Taking a plant molecule and altering it slightly produced a better drug. This approach, identifying active natural compounds and then modifying them, became a cornerstone of pharmaceutical development. Willow bark to aspirin is a story of refinement. Nature provided the blueprint. Chemistry made it better. Tannins in tea bind to proteins, creating astringency. Tannins are large, complex molecules with multiple hydroxyl groups. These groups form hydrogen bonds with proteins in saliva. When tannins bind to salivary proteins, the proteins precipitate, forming aggregates. This reduces the lubricating quality of saliva, creating a dry, puckering sensation in the mouth. Astringency is not a taste. It is a tactile sensation, a physical change in the mouth's texture. Tannins cause the same sensation in wine, unripe fruit, and dark chocolate. The effect is more pronounced with hot tea because heat increases tannin extraction from the leaves. Tannins serve a defensive function in plants. They make leaves less palatable and harder to digest. Herbivores that eat tannin-rich plants absorb fewer nutrients. Some animals avoid high tannin foods entirely. Milk reduces tea's astringency. The proteins in milk bind to tannins, preventing them from binding to salivary proteins. This is why tea with milk feels smoother and less drying. The chemistry is the same, but the tannins are occupied elsewhere. Tannins also affect nutrient absorption. They bind to iron and other minerals, reducing their availability. Drinking tea with meals can decrease iron absorption, which is relevant for people at risk of deficiency. Astringency is chemistry you can feel. Molecules reach into your saliva and alter its consistency. Taste happens on the tongue. Astringency happens throughout the mouth. Anthocyanins change color with pH, making hydrangeas blue or pink. Anthocyanins are pigments responsible for red, purple, and blue colors in many flowers and fruits. The molecule's structure includes a positively charged oxygen atom that can gain or lose hydrogen ions depending on pH. In acidic conditions, anthocyanins are red. In neutral conditions, they are purple. In alkaline conditions, they shift toward blue. Hydrangeas demonstrate this vividly. The same plant produces pink flowers in acidic soil and blue flowers in alkaline soil. Gardeners can alter flower color by adjusting soil pH with aluminum sulfate to increase acidity or lime to increase alkalinity. Aluminum also plays a role. In acidic soil, aluminum is more soluble. Hydrangeas absorb aluminum, which binds to anthocyanins and intensifies the blue color. Pink hydrangeas grown in aluminum-poor soil remain pink even if pH is adjusted. Anthocyanin color shifts are reversible. Add acid to blueberry juice and it turns red. Add base and it turns blue-green. The pigment molecules respond instantly to pH changes. The same molecule, in different chemical environments, produces different colors. Red cabbage is a pH indicator for the same reason. Its anthocyanins turn red in vinegar, purple in water, and green in baking soda. Chemistry students use cabbage juice to demonstrate acid-base chemistry because the color changes are dramatic and immediate. Color is not fixed. It is chemistry responding to the environment in real time. Essential oils are volatile terpenes that evaporate at room temperature. Terpenes are built from isoprene units, 5-carbon building blocks that can link in many ways. These molecules are small and nonpolar, which makes them evaporate easily. When you smell lavender, eucalyptus, or lemon, you are detecting terpenes drifting from the plant into the air. Plants produce terpenes for communication and defense. Some attract pollinators. Others repel herbivores or inhibit the growth of competing plants. Terpenes can also protect plants from heat stress by evaporating and cooling leaf surfaces. Essential oils are extracted by distillation or pressing. Steam carries volatile terpenes out of plant material. The steam is cooled and the oil separates from water. A small amount of plant material yields only a tiny volume of oil, which is why essential oils are concentrated and potent. Different plants produce different terpene profiles. Limonene, found in citrus peels, smells sharp and fresh. Linalool, found in lavender, smells floral and calming. Menthol, found in mint, smells cool and sharp. Each terpene has a distinct structure that determines its scent and properties. Terpene chemistry is ancient. These molecules appeared early in plant evolution and remain ubiquitous. They shape ecosystems by mediating interactions between plants, pollinators, herbivores, and competitors. What we experience as fragrance is communication, written in volatile molecules. Pigments absorb certain wavelengths and reflect others as color. A pigment molecule has a specific electronic structure. When light strikes it, electrons can absorb photons if the photon energy matches the energy gap between electron levels. The absorbed wavelengths disappear from the reflected light. What remains is the color we see. Red pigments absorb green and blue wavelengths, reflecting red. Blue pigments absorb red and yellow wavelengths, reflecting blue. Black pigments absorb nearly all wavelengths. White pigments scatter all wavelengths without absorbing them. The color of a pigment is determined entirely by which wavelengths it rejects. Pigments differ from dyes. Pigments are insoluble particles that sit on surfaces or are embedded in materials. Dyes dissolve and bond chemically to fibers or substrates. Paint uses pigments suspended in a binder. Fabric dye uses dissolved molecules that penetrate and bind to threads. The electronic structure that creates color often involves conjugated systems, alternating single and double bonds that allow electrons to move freely. The longer the conjugated chain, the lower the energy needed to excite electrons, and the longer the wavelength absorbed. This is why carotenoids, with their long conjugated chains, absorb blue and green light and appear yellow to red. Color is not an inherent property. It emerges from the conversation between light and electrons. Change the electronic structure slightly, and the color shifts. Add or remove a double bond. Substitute one atom for another, and a red pigment becomes orange or yellow. Prussian blue was the first synthetic pigment discovered by accident. In 1706, a German dye maker named Johann Jakob Diesbach was trying to create a red pigment. He used potash contaminated with animal blood. Instead of red, he produced an intense, deep blue. The contaminant contained iron from the blood, which reacted with other components to form iron ferrocyanide, or Prussian blue. Prussian blue is a coordination compound. Iron atoms are linked through cyanide groups, forming a three-dimensional lattice. The structure absorbs red and yellow light strongly, reflecting a rich blue. The pigment is stable, non-toxic, and inexpensive, making it immediately popular. Before Prussian blue, intense blue pigments were rare and costly. Ultramarine came from grinding lapis lazuli, a semi-precious stone imported from Afghanistan. Prussian blue provided an affordable alternative. It revolutionized painting, printing, and textile dyeing. The accidental discovery demonstrated that chemistry could create colors not easily found in nature. Artists no longer depended entirely on minerals, plants, and insects for their palettes. Synthetic chemistry began expanding the spectrum of available colors, a process that continues today. Prussian blue also has medical uses. It binds to certain radioactive isotopes and heavy metals, helping the body eliminate them. A pigment invented by accident for art became a treatment for poisoning. Titanium dioxide makes white paint bright by scattering all light. Most white pigments work by reflecting light diffusely. Titanium dioxide is exceptionally effective because its refractive index is very high. When light enters a particle of titanium dioxide, it bends sharply. As light exits and enters neighboring particles, it scatters in all directions. This scattering is so efficient that titanium dioxide hides whatever lies beneath it. A thin layer of titanium dioxide paint can cover a dark surface completely. No other white pigment matches its opacity and brightness. Titanium dioxide is also chemically stable. It does not yellow with age or degrade in sunlight. It is non-toxic, unlike lead, white, which was once the dominant white pigment, but caused lead poisoning in painters and factory workers. Titanium dioxide appears not only in paint, but also in sunscreen, toothpaste, and food. In sunscreen, it scatters UV light, protecting skin. In toothpaste, it provides whiteness. In food, it brightens candies, frosting, and powdered sugar. The pigment is made by processing titanium ore, either ilmenite or rutile. The ore is refined through chemical reactions that produce pure titanium dioxide crystals. Different crystal structures, rutile and anatase, have slightly different properties. Rutile is preferred for paint because it scatters light more effectively. Whiteness is not absence of color. It is all colors scattered equally, and titanium dioxide achieves this better than any other substance. Carbon black is the most common pigment, made from incomplete combustion. When hydrocarbons burn without enough oxygen, carbon atoms link into tiny particles of nearly pure carbon. These particles are collected as a fine black powder. The particles absorb light across the entire visible spectrum, making carbon black one of the darkest materials known. Carbon black is not the same as charcoal or soot, though all are forms of carbon. Carbon black is manufactured under controlled conditions to produce particles of specific size and structure. Smaller particles create deeper, bluer blacks. Larger particles create warmer, browner blacks. The pigment is used in inks, paints, plastics, and rubber. Most car tires are black because they contain large amounts of carbon black, which reinforces the rubber and improves durability. Printer ink and newspaper ink rely on carbon black for their intense, opaque blackness. Carbon black has been used since ancient times. Cave paintings made with charcoal contain carbon black. Egyptian ink made from lamp black, soot collected from oil lamps, produced writing that remains legible thousands of years later. The pigment is permanent because carbon does not degrade or fade. In modern manufacturing, carbon black is produced by burning oil or natural gas in reactors with controlled airflow. The particles form in the flame and are carried away by gas, then collected on filters. The process is efficient and produces pigment in vast quantities. Blackness is not simply the absence of light, it is complete absorption, and carbon structure makes it unsurpassed at swallowing photons. Indigo dye becomes blue only after exposure to oxygen. The indigo plant produces a precursor molecule that is colorless and water-soluble. When fabric is dipped in a vat of indigo solution, this precursor soaks into the fibers. When the fabric is lifted into the air, oxygen reacts with the precursor, converting it into indigotin, the blue pigment. The color appears as you watch, fading in from pale green to deep blue. Indigotin is insoluble in water, which is why it must be applied in its reduced colorless form. Once oxidized, it is trapped in the fabric. This makes indigo remarkably durable. The dye does not wash out because it is not soluble. It can only be removed by abrasion or by breaking down the molecule chemically. Denim jeans owe their color to indigo. The dye penetrates only the surface of the cotton threads, leaving the core white. As jeans are worn and washed, the surface indigo wears away, creating the characteristic fading pattern. The more the jeans are worn, the lighter they become, exposing the white core. Synthetic indigo is now more common than natural indigo. The structure is identical, but synthetic indigo is cheaper and more consistent. The synthesis was developed in the late 1800s, ending the dominance of indigo plantations. a dye that appears only in air, that becomes permanent through oxidation, that fades beautifully with wear. Indigo's chemistry makes it uniquely suited for a fabric meant to age. Morvain was the first synthetic dye launching the chemical industry. In 1856, 18-year-old William Henry Perkin was trying to synthesize quinine, a malaria treatment from coal tar. The experiment failed, producing a black sludge. Perkin noticed the sludge left a vivid purple stain. He extracted the colored compound and tested it on silk. The fabric took a brilliant, lasting purple. Before Morvain, purple dyes were rare and expensive. Tyrian purple came from sea snails, requiring thousands of snails for a small amount of dye. Only royalty could afford it. Perkin's synthetic purple made from coal tar could be produced cheaply in large quantities. He patented the dye, built a factory, and became wealthy. Morvain's success inspired other chemists to search for synthetic dyes. Within decades, chemists synthesized dyes in every color, replacing most natural dyes. The synthetic dye industry became the foundation of the modern chemical industry, leading to pharmaceuticals, plastics, and explosives. The molecular structure of Morvain is complex, and Perkin did not fully understand it. He succeeded through experimentation and observation, not complete theoretical knowledge. Later chemists elucidated the structure and learned to design dyes systematically. A failed experiment produced a fortune and an industry. Perkins saw potential in what others might have discarded. The stain became a revolution. Fluorescent colors absorb UV light and re-emit it as visible light. Normal pigments reflect light passively. Fluorescent pigments actively emit light after absorbing higher energy photons. A fluorescent molecule absorbs a UV photon, which excites electrons to a high energy state. The electrons drop back down, releasing energy as visible light. This process makes fluorescent colors appear unusually bright. They do not just reflect ambient light. They convert invisible UV light into additional visible light. In sunlight, which contains UV, fluorescent colors seem to glow. They emit more visible light than falls on them, which seems impossible, but is simply energy conversion. Highlighter markers use fluorescent dyes. Under normal light, they are bright. Under UV light, such as a black light, they glow intensely. Safety vests and traffic cones use fluorescent colors to maximize visibility. The colors stand out even in dim conditions because they generate their own light from environmental UV. Fluorescent molecules must have specific electronic structures that allow rapid, efficient re-emission of photons. Not all molecules fluoresce. Those that do are carefully selected or designed for maximum brightness and stability. Fluorescence is not phosphorescence. Fluorescent materials emit light only while exposed to UV. Phosphorescent materials absorb energy and release it slowly over time, continuing to glow after the light source is removed. Glow-in-the-dark toys use phosphorescence, not fluorescence. Fluorescent colors cheat. They harness invisible energy and make it visible, glowing brighter than physics should allow from reflection alone. Iridescence comes from light interference in layered structures, not pigment. A soap bubble, a beetle shell, and an oil slick all shimmer with changing colors, yet they contain no pigments. The colors arise from the way light waves interact with thin, transparent layers. When light strikes a thin film, some reflects from the top surface, and some penetrates and reflects from the bottom surface. The two reflected waves travel slightly different distances. If the waves are in phase, they reinforce each other, producing bright color. If out of phase, they cancel and the color disappears. Which wavelengths reinforce depends on the film's thickness and the angle of viewing. This is why iridescent colors shift as you move. Changing the angle changes the path difference, which changes which wavelengths interfere constructively. A beetle shell flashes green, then blue, then purple as you tilt it. Iridescence in nature often comes from layered structures in scales, feathers, or shells. Butterfly wings contain stacks of thin layers separated by precise distances. Peacock feathers have similar structures. These layers act as interference filters, selecting specific wavelengths to amplify. Humans have learned to mimic this. Some paints contain flakes of mica or other materials coated with thin layers of metal oxides. The layers produce color through interference, creating shimmering, color-shifting effects in automotive and cosmetic applications. Iridescence is geometry, not chemistry. The color exists in the structure, not the substance. Destroy the layers, and the color vanishes. Yet the material remains chemically unchanged. As we come to the end of this gentle journey through chemistry, you might sense a theme emerging from the molecules. Everything around you is in conversation. Water speaking to salt, oxygen courting iron, light breaking bonds that heat alone could never touch. These exchanges happen constantly, silently, at scales too small to see, but large enough to shape the world you inhabit. Chemistry is not distant or abstract. It is the language your coffee uses to wake you, the vocabulary of soap lifting grease from your hands, the grammar of bread rising in an oven. It explains why autumn arrives in color, why metal rusts, why ice floats and protects the life below. The same principles govern a candle flame, a battery, a leaf turning sunlight into sugar. We have wandered through kitchens and skies, through pigments and polymers, through rust and respiration. Each fact is a small window into the molecular architecture that supports every moment of existence. Hydrogen bonds holding water together. Electrons jumping between energy levels to create color. Proteins folding into shapes that determine whether dough rises or an egg sets. All of it, every transformation, follows rules written in atomic interactions. If you enjoyed this exploration, I invite you to subscribe, to share this with someone who might find comfort or curiosity here, or simply to leave a thought below. It helps other sleepy minds discover these quiet journeys through science. One peaceful soul at a time. But for now, there is nothing left to do but rest. Let your breathing deepen and slow. Feel the weight of your body sinking into stillness. Allow your thoughts to drift like smoke, formless and unhurried. Let the chemistry of sleep take over, the gentle cascade of neurotransmitters and neural rhythms that will carry you into rest. The molecules will continue their work without you. Water will keep dissolving, oxygen will keep bonding, light will keep scattering. The invisible world will hum along, patient and tireless, waiting for you when you wake. Sleep well, and good night.